Welcome to The Sleepless Universe. In this video, we embark on a calm but fascinating journey through our entire solar system, from the blazing heart of the sun to the frozen edge of the Oort cloud. Along the way, we'll uncover the hidden wonders of each world, explore mysteries you may have never heard of, and drift slowly through the beauty of space. Before we set off, write in the comments where you're watching from and what time it is for you. If you enjoy this kind of relaxing cosmic exploration, I'd truly appreciate a like and a subscription. Now, sit back, relax, and let's begin our journey through the solar system. The birth of our solar system. If you could step back in time 4.5 billion years, you would not recognize the place we now call home. There would be no blue oceans shimmering in the sunlight, no continents drifting lazily on tectonic plates, and no soft, pale moon glowing in the night sky. Instead, you would find yourself drifting in a vast cloud of gas and dust, a cosmic nursery where countless grains of matter floated silently, waiting for gravity to decide their fate. This cloud was known as the solar nebula, and it held within it all the raw materials that would one day form the sun, the planets, their moons, the asteroids, and even the comets that streak across our skies. The story begins in the quiet outskirts of our galaxy, in a spiral arm where stars are born in great clouds of hydrogen and helium. Somewhere in one of these regions, a shock wave, possibly from the explosion of a nearby star, disturbed a massive cloud of interstellar gas and dust. That disturbance caused the cloud to collapse in on itself under the irresistible pull of gravity. As the cloud fell inward, it began to spin, much like a figure skater pulling in their arms to spin faster. Over time, the material flattened into a rotating disk, with most of the mass concentrating in the center. At the heart of this swirling disk, matter became so densely packed that temperatures soared to millions of degrees. The pressure grew immense, and eventually, nuclear fusion ignited. Hydrogen atoms began fusing into helium, releasing vast amounts of energy. Our sun was born, a newborn star that blazed brilliantly in the cosmic darkness. Around it, in the cooler outer regions of the disk, the leftover gas and dust began sticking together, grain by grain, forming larger and larger clumps. Some of these clumps became planetesimals, small, rocky or icy bodies that could grow into planets. In the inner part of the disk, where it was too warm for ice to survive, rocky worlds began to take shape. Here, metals and silicates condensed out of the gas, slowly building up the foundations of what would become Mercury, Venus, Earth, and Mars. Further out, beyond what astronomers call the frost line, the temperature was cold enough for ice to form. In these regions, planetesimals could grow much larger, as they not only accumulated rock and metal, but also vast amounts of frozen water, methane, and ammonia. These became the seeds of the giant planets: Jupiter, Saturn, Uranus, and Neptune. It's important to realize that this was not a peaceful process. The early solar system was a chaotic place, filled with constant collisions. Some of these impacts were gentle, allowing bodies to merge and grow. Others were catastrophic, shattering objects into pieces that later reassembled, or were swept away by gravitational forces. The Earth itself likely experienced one of the most dramatic collisions in its history, when a Mars-sized body, often called Theia, slammed into it. The debris from this impact eventually coalesced into our moon, giving us not only a beautiful nighttime companion, but also a stabilizing influence on our planet's tilt and climate. While the planets were forming, the sun was far from quiet. It unleashed powerful solar winds, streams of charged particles that blasted through the young system. These winds pushed away much of the remaining gas and dust, preventing further large-scale accretion and effectively halting the formation of new planets. What remained were the planets we know today, along with countless smaller bodies, asteroids in the belt between Mars and Jupiter, icy comets in the Kuiper Belt and Oort cloud, and other remnants of that ancient construction process. The arrangement of planets in our solar system is not random. The inner rocky worlds formed close to the sun, because only materials with high melting points could survive the heat. The gas giants formed further out, where ices could remain stable, allowing them to grow large enough to capture thick atmospheres of hydrogen and helium. Beyond them, the ice giants, Uranus and Neptune, formed from smaller cores that still managed to grab significant amounts of gas before the solar winds swept the rest away. But our solar system hasn't always looked exactly as it does now. Astronomers believe that the giant planets may have migrated from their original positions, reshaping the architecture of the system. This movement could explain the scattering of icy bodies into the distant Kuiper belt and the delivery of water-rich comets to the early Earth. Without this migration, our planet might never have received the life-sustaining water that fills our oceans today. Even now, the solar system remains a dynamic place. The planets travel in elliptical orbits, locked in a delicate gravitational dance with the sun and with each other. Asteroids sometimes stray from their usual paths. Comets return on long journeys from the outermost reaches. And dust from countless collisions continues to drift through space. Our home star itself is not immortal. It is about halfway through its life, steadily fusing hydrogen into helium in its core. In another 5 billion years, it will swell into a red giant, swallowing Mercury and Venus, and possibly even the Earth. After that, it will shed its outer layers, leaving behind a dense white dwarf surrounded by a glowing shell of gas. But for now, the sun remains stable, and the planets continue their orbits, just as they have for billions of years. When you look up at the night sky, you are seeing a system that has survived cosmic violence, planetary migrations, and the relentless forces of gravity. It is a reminder that our existence is tied to ancient processes that began long before humans ever walked the Earth. And so, as we set off on our journey through the solar system, it's worth remembering that everything we will encounter, the planets, the moons, the asteroids, are chapters in this grand story. Each one has its own history, shaped by collisions, eruptions, and transformations. Together, they tell the tale of a cosmic neighborhood that has been in motion for billions of years and will continue to evolve long after we are gone. In understanding the birth of our solar system, we also gain insight into the formation of other planetary systems scattered throughout our galaxy. Astronomers have observed hundreds of young stars still surrounded by disks of dust and gas, places where planets are actively taking shape. These so-called protoplanetary disks are snapshots of the process that shaped our own neighborhood, allowing us to compare, contrast, and refine our theories. In some systems, we see planets forming much closer to their stars than Mercury is to the Sun, creating scorching hot worlds. In others, massive gas giants orbit far from their central star, similar to our own Jupiter and Saturn. These observations suggest that while the underlying physics of planet formation is universal, the details can vary dramatically, leading to a staggering variety of planetary systems. In the early days of our solar system, the interplay between gravity, heat, and motion determined the architecture we see today. Gravitational interactions between forming planets often led to close encounters, causing dramatic shifts in orbits. Some worlds were flung out into the depths of interstellar space, becoming so-called rogue planets, adrift in the darkness without a parent star. Others were swallowed by the sun or collided with larger bodies, merging to form new worlds. The survivors of this cosmic chaos settled into relatively stable orbits, but their scars remain visible in craters, mountain ranges, and tilted axes. One of the remarkable aspects of our solar system's story is how much it has been shaped by chance events. For example, without the colossal impact that formed the moon, Earth might have evolved into a very different world. The moon's gravitational influence has helped stabilize Earth's axial tilt, preventing extreme swings in climate that could have hindered the development of complex life. Similarly, the presence of Jupiter has acted as both a protector and a threat. Its immense gravity can deflect dangerous comets and asteroids away from Earth, but it can also send them hurtling toward us. This dual role underscores the delicate balance in which we live. The solar system also contains a number of leftovers from its formation, relics that never became planets. The asteroid belt, located between Mars and Jupiter, is one such example. While it contains hundreds of thousands of rocky bodies, their combined mass is far less than that of our moon. This is because Jupiter's gravitational pull prevented these objects from coalescing into a single planet. Further out, past Neptune, lies the Kuiper belt, a region filled with icy bodies including Pluto, Eris, and other dwarf planets. Even farther still is the hypothetical Oort cloud. a vast shell of icy objects that may extend halfway to the nearest stars. This distant region could be the source of the long-period comets that occasionally grace our skies, their glowing tails stretching across the heavens. Another fascinating aspect is the way the sun's energy has influenced every corner of the solar system. Its light and heat drive weather patterns, sculpt landscapes, and even affect the chemistry of planetary atmospheres. On Earth, sunlight fuels photosynthesis, the process that sustains nearly all life. On Mars, it stirs seasonal dust storms that can envelop the planet for months. On icy moons like Europa and Enceladus, sunlight plays a lesser role, but the gravitational pull of giant planets creates tidal forces that generate internal heat, possibly keeping subsurface oceans liquid and potentially habitable. When we think about the solar system's birth, we should also consider its future. Over the next few billion years, subtle changes will occur. The sun's brightness will slowly increase, altering climates and perhaps pushing the habitable zone farther outward. Moons will drift away from their parent planets due to tidal interactions. Some asteroids may collide with planets, reshaping surfaces in an instant. And in the far future, when the sun exhausts its nuclear fuel, the solar system will undergo one final transformation. As the sun swells into a red giant, its outer layers will engulf the inner planets. Earth may be incinerated, or if it survives, it will become a barren, scorched world. Eventually, the sun will shed its outer layers, creating a beautiful but short-lived planetary nebula before contracting into a dense white dwarf that will gradually cool over trillions of years. Despite this eventual end, our solar system is still in a relatively stable and hospitable phase of its life. The planets maintain their orbits with predictable regularity, and the sun provides a steady stream of energy. This stability has allowed life to flourish on at least one world, and perhaps it exists on others, hidden beneath ice or within clouds. As we set out to explore our cosmic neighborhood, we are not just learning about other planets. We are learning about our own origins and place in the universe. The concept of time in this story is almost impossible to grasp. Human history spans only a few thousand years, a mere blink compared to the solar system's age. From the perspective of the planets, continents drifting, ice ages coming and going, and civilizations rising and falling are all brief, passing events. Even now, as you listen, the planets continue their ancient journeys, unhurried and indifferent to our fleeting presence. This chapter of our journey is just the beginning. In the coming chapters, we will leave this overview behind and travel outward from the blazing heart of the sun, visiting each world in turn. We will see scorched landscapes and frozen plains, swirling storms and rings of ice, volcanoes that erupt not with lava, but with water. We will uncover strange moons that defy expectations, dwarf planets that challenge our definitions, and distant regions where the sun is just another bright star in the sky. The solar system is more than just a collection of planets and rocks. It is a living, evolving system, shaped by forces both gentle and violent. Every crater tells a story of impact, every canyon a tale of erosion, every orbit a history of gravitational negotiation. And all of it began with a collapsing cloud of gas and dust, a chance event in a quiet corner of the galaxy that gave rise to everything we know. So, as we set sail on this cosmic voyage, let's remember, the light from the sun that warms your skin began its journey 8 minutes ago. But the atoms in your body were forged in ancient stars long before the solar system existed. We are, in a very real sense, children of the stars, born from their remnants, living under their light, and destined one day to return to the cosmos from which we came, the sun, our local star. If the solar system were a grand stage, the sun would be its dazzling spotlight, illuminating every actor and shaping the very nature of the performance. It is the gravitational anchor around which every planet, moon, asteroid, and comet revolves. It is the engine that powers our seasons, drives weather patterns, and enables life to exist on Earth. Yet, for all its brilliance, the sun is also an ordinary star, one among hundreds of billions in our galaxy. Ordinary, yes, but for us, utterly irreplaceable. The sun is, by astronomical classification, a G-type main sequence star, sometimes casually referred to as a yellow dwarf. It is not truly yellow, but emits white light that appears yellowish from Earth's surface due to our atmosphere scattering shorter wavelengths of light. Its mass makes up more than 99.8% of the total mass of the entire solar system. That mass, almost unimaginably large, is what produces the intense gravity that keeps all the planets in their orbits. Without the sun's pull, the solar system would dissolve into chaos, its members drifting into the cold void of interstellar space. But the sun is more than just a massive ball of gas. It is a nuclear fusion reactor on a truly colossal scale. In its core, where temperatures reach about 15 million degrees Celsius, hydrogen nuclei slam together with enough force to overcome their natural repulsion. They fuse into helium, releasing energy in the form of photons and neutrinos. This process has been ongoing for about 4.6 billion years and will continue for roughly another 5 billion. The energy produced in the sun's core takes an astonishing amount of time to reach its surface. A photon created deep within might take tens of thousands of years, bouncing from particle to particle, before finally escaping into space as sunlight. Once free, it races toward Earth in just over 8 minutes, bathing our world in warmth and light. The sun is composed mostly of hydrogen, about 74% by mass, and helium, about 24%, with small amounts of heavier elements like oxygen, carbon, and iron. These heavier elements are the remnants of earlier generations of stars that lived and died before our sun was born. In this way, our sun, like all stars, is a link in a cosmic chain of creation and destruction that stretches back to the earliest days of the universe. Its structure is layered, each region playing a critical role in the sun's behavior. At the very center lies the core, the furnace of nuclear fusion. Surrounding the core is the radiative zone, where energy is transferred outward through countless photon interactions. Beyond that lies the convective zone, where heat moves more like boiling water, with huge currents of plasma carrying energy toward the surface. The sun's visible surface, the photosphere, is where sunlight escapes into space. Above it, the thin chromosphere and the outermost corona, visible during a total solar eclipse, extend far into space, with temperatures unexpectedly hotter than the surface itself. The sun's corona is a subject of ongoing mystery and study. While the photosphere is around 5,500 degrees Celsius, the corona can reach several million degrees. This counterintuitive temperature rise remains one of solar physics' great puzzles, with magnetic waves and reconnection events likely playing a role. The corona is also the source of the solar wind, a stream of charged particles that flows outward in all directions. This wind shapes the heliosphere, a vast bubble of solar influence that extends well beyond the orbit of Pluto. The sun is not a static object. Its surface is alive with activity. Sunspots, flares, and prominences dance across it, driven by powerful magnetic fields. Sunspots are cooler, darker regions caused by intense magnetic activity that inhibits convection. Solar flares are sudden bursts of energy that release massive amounts of radiation and can impact Earth's magnetosphere, sometimes causing spectacular auroras. More powerful events, called coronal mass ejections, hurl billions of tons of charged particles into space. If aimed at Earth, these can disrupt satellites, power grids, and communication systems. A reminder that while the sun sustains life, it can also pose risks to our technological civilization. The sun's activity follows an approximately 11-year cycle, with periods of high and low magnetic activity. During solar maximum, sunspots and flares are more frequent. During solar minimum, the sun's surface appears calmer. This cycle influences space weather, which in turn can affect everything from astronaut safety to the performance of navigation systems. For life on Earth, the sun is the ultimate provider. Its energy drives the water cycle, powers photosynthesis in plants, and warms the planet enough to keep water in liquid form. Slight changes in the sun's output can have measurable effects on climate. Over geological timescales, variations in solar radiation have contributed to ice ages and warmer interglacial periods. On shorter timescales, even small dips or increases in solar activity can subtly influence atmospheric circulation. In cultural terms, humanity has revered the sun since the dawn of civilization. Ancient Egyptians worshipped it as the god Ra, The Aztecs offered sacrifices to ensure its continued journey across the sky. Countless myths and legends depict it as a divine being or a life-giving force. Our modern scientific understanding does not diminish its importance. If anything, it deepens our appreciation of just how finely balanced our relationship with the sun truly is. Yet, the sun's life is finite. It is currently in the middle of its main sequence phase, steadily converting hydrogen into helium. Over the next billions of years, the hydrogen in its core will gradually be depleted. When that happens, the core will contract and heat up, triggering the fusion of helium into heavier elements like carbon and oxygen. The outer layers will swell, transforming the sun into a red giant. This expansion will likely engulf Mercury and Venus, and possibly Earth. The surface temperature will drop, but the sun's size will increase dramatically, becoming hundreds of times its current diameter. After this red giant phase, the sun will shed its outer layers into space, creating a glowing shell of gas, a planetary nebula, while the core remains as a white dwarf, an Earth-sized remnant with the mass of the sun. Over trillions of years, this white dwarf will cool and fade, becoming a cold, dark object. Long before that, however, the solar system as we know it will have changed beyond recognition. Understanding the sun's nature is more than just an academic pursuit. It is vital for predicting and preparing for the impacts of its variability on our planet. From the reliability of power grids to the safety of astronauts, solar science informs a wide range of practical concerns. Observatories on Earth and in space, like the Solar Dynamics Observatory and the Parker Solar Probe, are constantly monitoring the sun, capturing high-resolution images, and measuring the solar wind to better understand its behavior. And yet, for all the sophisticated instruments and complex models, there is still something profoundly humbling about simply watching the sun rise. Every morning, it climbs over the horizon, painting the sky in shades of gold and crimson, a ritual as old as the Earth itself. That daily act connects us to the ancient peoples who first looked skyward and felt its warmth, and to the scientists today who dedicate their lives to unraveling its secrets. The sun's influence extends far beyond the 8 major planets. Its gravity holds comets in vast reservoirs at the solar system's edge, such as the Kuiper Belt and the hypothetical Oort cloud. When comets are nudged inward by gravitational interactions, their icy surfaces begin to sublimate in the sun's warmth, forming bright tails that always point away from the star. These fleeting visitors are reminders of the sun's reach, capable of shaping the destiny of objects trillions of kilometers away. Closer to home, the sun interacts constantly with Earth's magnetic field. When charged particles from the solar wind collide with atoms in our upper atmosphere, they excite those atoms, causing them to emit light. This is what creates the auroras, ethereal curtains of green, red, and purple that dance near the poles. While beautiful, these events also serve as visual evidence of the invisible forces linking Earth to its star. During periods of intense solar activity, auroras can be seen much farther from the poles, sometimes as far as the tropics. The sun's variability is one reason why scientists pay close attention to its patterns. Space weather forecasting is an emerging field aimed at predicting solar flares and coronal mass ejections. These predictions are critical for safeguarding satellites, navigation systems, and astronauts aboard the International Space Station. In extreme cases, a powerful solar storm could even cause widespread power outages on Earth, similar to the 1859 Carrington event, which disrupted telegraph systems worldwide. In our technology-dependent age, a repeat of such an event could have far more serious consequences. From a physical standpoint, the sun is a near-perfect sphere of hot plasma, held together by its own gravity. Its surface appears calm from a distance, but up close, it is seething with motion. Convection cells called granules, each roughly the size of Texas, constantly rise and fall as heat from the interior makes its way outward. Above them, magnetic fields twist and snap, releasing bursts of energy. Sunspots, which may appear small through a telescope, are often larger than Earth itself. These features shift and change over days and weeks, a reminder that the sun is not a static object, but a living, dynamic system. Its immense heat and light sustain our biosphere, but the sun also poses challenges to space exploration. Any spacecraft venturing close to it must endure extreme temperatures and intense radiation. The Parker Solar Probe, launched in 2018, is the closest human-made object to the Sun, protected by a cutting-edge heat shield capable of withstanding temperatures over 1,300 degrees Celsius. This probe is gathering unprecedented data about the Sun's corona and solar wind, helping scientists address long-standing questions about how energy moves through the Sun's outer atmosphere. In terms of its place in the universe, the Sun is relatively unremarkable. It is not particularly large compared to other stars, nor is it especially hot or luminous. Stars like it are common in the Milky Way. And yet, from our perspective, it is extraordinary. Without it, life as we know it could not exist. Its stability has given Earth the time and conditions needed for complex life to evolve. If the Sun had been slightly more massive, it would have burned hotter and faster, shortening the window for life to develop. If it had been smaller, it might not have provided enough warmth to keep Earth's water from freezing. We live in a sweet spot, a narrow band of conditions that has allowed our planet to flourish. The Sun also plays a central role in the intricate dance of the solar system's dynamics. Its gravity governs the orbital periods of the planets, which in turn create resonances and patterns that can influence the stability of smaller bodies like asteroids. Even the tilt of a planet's axis can be subtly shaped by the gravitational interactions within this system, which all trace back to the Sun's dominant mass. Culturally, the Sun continues to inspire art, literature, and philosophy, from the concept of heliocentrism in the Renaissance, which revolutionized our understanding of the cosmos, to modern ecological movements that harness solar power. The Sun is woven deeply into human history. Solar energy technology has transformed the Sun into a direct provider of electricity, allowing us to capture a tiny fraction of its immense output for our own purposes. Every second, the Sun emits more energy than humanity has used in its entire history. Yet the amount that actually reaches Earth is just a small portion of its total. This abundance has sparked visions of a future where much of our civilization runs on clean, renewable solar power. Looking ahead, our relationship with the Sun will continue to evolve. Spacecraft will study it more closely. Humans may one day build stations in orbit near Mercury to harness its energy directly, and our understanding of stellar physics will deepen. But even as we advance technologically, the Sun will remain a constant in our lives, a bright, steady beacon in the sky, rising and setting each day as it has for billions of years. When we imagine traveling outward from Earth, the Sun is always our point of reference. Astronauts leaving our planet for the Moon or Mars will still see it as a familiar presence in the sky. Even the distant spacecrafts, Voyager 1 and Voyager 2, now in interstellar space, still feel the faint touch of the Sun's gravity and its dwindling solar wind. Its influence stretches across a vast domain, marking the boundary between our solar system and the galaxy beyond. And yet, the Sun is but one star among countless others. In the night sky, each point of light is another sun, some larger, some smaller, some older, some younger. Many of them host their own systems of planets, moons, and perhaps life. In that sense, studying our Sun is also a way of understanding stars everywhere. It is a bridge between the intimacy of our local environment and the vast, unknowable reaches of the cosmos. As we conclude our focus on the Sun, it's worth pausing to appreciate the simple fact of its constancy. Through every chapter of human history, from the first stone tools to the latest space telescopes, it has been there, steady, reliable, and life-giving. The Sun's story is far from over, but for now, it continues to shine in the prime of its life, casting its light across the solar system and reminding us that, while we may be small in the grand scale of the universe, we are part of something magnificent. Mercury, the scorched world. If you could stand on the surface of the innermost planet of our solar system, you would find yourself in a place of extremes. The Sun would loom more than twice as large in the sky as it does from Earth, blazing with a heat so intense that it could melt lead. And yet, if you waited for night to fall, you would be plunged into a cold so deep it could freeze most gases solid. This is Mercury, a small, airless world locked in a perpetual struggle between scorching heat and frigid darkness. Mercury is the smallest of the 8 major planets, just a bit larger than Earth's moon. With a diameter of about 4,880 kilometers, you could line up almost 3 Mercuries across the width of our planet. Despite its modest size, Mercury is surprisingly dense, with a large metallic core that makes up roughly 85% of its volume. Scientists believe this oversized core may be the result of a violent past, possibly a giant collision that stripped away much of Mercury's original crust and mantle, leaving behind a planet dominated by metal. Orbiting the Sun at an average distance of only 58 million kilometers, Mercury completes a full revolution in just 88 Earth days. However, its day, defined as one rotation relative to the Sun, is much longer. Due to a curious 3-to-2 spin-orbit resonance, Mercury rotates 3 times for every 2 trips around the Sun. This means that one Mercurian day from sunrise to sunrise lasts about 176 Earth days. This slow rotation, combined with the lack of a thick atmosphere, allows the planet's surface to experience extreme temperature swings, from over 430 degrees Celsius in daylight to below minus 180 degrees Celsius at night. Looking at Mercury's surface, you would see a world shaped by impacts and ancient volcanic activity. Its terrain is heavily cratered, resembling the moon's battered face. Some of these craters are vast, like the Caloris Basin, one of the largest impact structures in the solar system, measuring about 1,550 kilometers across. The force of the impact that created it was so immense that it sent shockwaves around the planet, forming strange hilly terrain directly opposite the impact site. In between the craters are vast plains, many of which were formed by ancient lava flows that once seeped from the planet's interior, filling low-lying areas with dark basaltic rock. Because Mercury has no significant atmosphere, its skies are always black, even in the daytime. There are no clouds to soften the sun's glare, no air to scatter its light. Standing on the surface, you would be surrounded by silence. Sound cannot travel in a vacuum. The horizon would curve noticeably beneath your feet, a reminder of the planet's small size, and the sun would rise and set in a way unlike anything on Earth. Due to the planet's slow rotation and elliptical orbit, the sun appears to perform a strange dance in the sky, even briefly reversing direction near sunrise and sunset. Although Mercury is close to the sun, it is not the hottest planet in the solar system. That title belongs to Venus, whose thick atmosphere traps heat and a runaway greenhouse effect. Mercury, with no such blanket, radiates its daytime heat into space as soon as the sun sets, causing the extreme nighttime cold. This lack of atmosphere also means that Mercury is constantly bombarded by micrometeorites, which slowly sandblast its surface, and by the solar wind, which can strip atoms from the planet's thin exosphere. That exosphere, Mercury's atmosphere in the loosest sense, is a tenuous envelope of atoms knocked from the surface by the solar wind and impacts. It is composed mainly of oxygen, sodium, hydrogen, helium, and potassium, but it is so thin that its individual atoms rarely collide. In many ways, it behaves more like a comet's tail than a planetary atmosphere. Mercury's proximity to the sun also makes it an important object of study for understanding how solar radiation and gravity affect a planet's evolution. It experiences a strong gravitational pull from the sun, resulting in a highly elliptical orbit that shifts over time in a way predicted by Einstein's general theory of relativity. Observations of Mercury's orbit in the 19th century provided one of the first confirmations of Einstein's groundbreaking theory. Despite its harsh environment, Mercury is not entirely without surprises. In 2012, NASA's Messenger spacecraft confirmed that water ice exists in permanently shadowed craters near the planet's poles. These regions never see sunlight due to Mercury's slight axial tilt of only 0.034 degrees, allowing them to remain cold enough to preserve ice for billions of years. The ice is likely mixed with dark organic compounds, possibly delivered by comets or asteroids. This discovery suggests that even the most unlikely worlds can harbor pockets of chemical ingredients important to the story of the solar system. From a historical perspective, Mercury has been a challenging planet to explore. Its closeness to the sun makes it difficult for spacecraft to reach and operate there, as they must battle both the sun's gravity and its intense heat. Only 2 missions have visited Mercury so far. NASA's Mariner 10 in the 1970s, which flew by the planet 3 times, and the Messenger mission, which orbited Mercury from 2011 to 2015. These missions transformed our understanding of this small world, mapping its surface in detail, analyzing its composition, and uncovering evidence of its geological past. Today, the European Space Agency and the Japan Aerospace Exploration Agency are collaborating on the Bepi-Colombo mission, currently en route to Mercury. Scheduled to arrive in 2025, it will study the planet's magnetic field, interior structure, and surface composition, building on the legacy of its predecessors. Mercury's weak but present magnetic field, unique among the inner rocky planets except for Earth, remains a puzzle. How such a small planet can maintain a molten core capable of generating this field is still not fully understood. Mercury's magnetic field is only about 1% as strong as Earth's, but its existence raises fascinating questions about the planet's interior. For a magnetic field to be generated, a planet typically needs a molten, electrically conductive core and some form of internal motion to create a dynamo effect. Mercury's small size should mean it has cooled and solidified long ago, but evidence suggests that at least part of its iron core remains liquid. One hypothesis is that the planet's high sulfur content lowers the melting point of the core's materials, allowing it to stay molten much longer than expected. The planet's interior is thought to be structured in 3 main layers: a massive metallic core, a silicate mantle, and a thin rocky crust. The crust is only a few tens of kilometers thick, making it proportionally much thinner than Earth's. This thin shell has been shaped by dramatic forces in the past. As Mercury's interior cooled over billions of years, it contracted, causing the surface to wrinkle and buckle. This created long cliffs, called lobate scarps, some stretching for hundreds of kilometers and rising over a kilometer high. These scarps are visible even today and tell a story of a planet slowly shrinking as it loses internal heat. The surface itself is a geological time capsule, with no atmosphere to erode craters and few geological processes to resurface the land. Mercury has preserved evidence of ancient impacts dating back billions of years. The heavily cratered highlands speak of an era known as the Late Heavy Bombardment, when the inner planets were pummeled by asteroids and comets. This period shaped not only Mercury, but also the Moon, Mars, and Earth, possibly delivering water and organic molecules essential for life to our planet. Although Mercury is inhospitable by any human standard, studying it helps scientists understand the boundaries of La's planetary habitability. By examining a world with almost no atmosphere, extreme temperature fluctuations, and a magnetic field far weaker than Earth's, researchers can better grasp what makes our own planet so uniquely suited to life. Mercury also serves as a laboratory for studying how planets evolve under intense solar radiation. This knowledge is valuable for understanding exoplanets found close to their stars, worlds that may be even hotter and more extreme than Mercury itself. From an observer's perspective, Mercury can be a tricky planet to spot in the sky. Because it orbits so close to the Sun, it is never visible in the middle of the night. Instead, it appears briefly in the twilight, either just before sunrise or just after sunset, depending on whether it is on the morning or evening side of its orbit. Ancient astronomers were aware of Mercury, but often thought they were observing 2 different stars, one appearing in the morning and one in the evening, until they realized both were the same planet. Its quick movement across the sky compared to other celestial bodies inspired its name, taken from the Roman messenger god known for his swiftness. One of the most fascinating optical events involving Mercury is the transit, when the planet passes directly between Earth and the Sun. During a transit, Mercury appears as a small black dot, slowly crossing the Sun's bright face. These events are relatively rare, occurring about 13 to 14 times per century, and they provide astronomers with valuable opportunities to study the planet's orbit and refine our understanding of celestial mechanics. Looking to the future, the Bepi-Colombo mission promises to answer many lingering questions about Mercury. By mapping its surface in greater detail, probing its magnetic field, and measuring the composition of its exosphere, scientists hope to uncover the full story of how this tiny world formed and evolved. Such research could also shed light on why Mercury is so different from the other rocky planets, and whether its peculiar characteristics are common in other planetary systems. The study of Mercury also has practical benefits for humanity's long-term exploration goals. While no one is proposing to colonize Mercury, it is simply too hostile. Its surface and polar regions could one day serve as bases for solar observation or resource extraction. The abundant sunlight could power scientific outposts, and the polar ice could provide water for future missions deeper into the solar system. In this way, even a scorched and barren planet could play a role in our expansion beyond Earth. When we think about Mercury in the context of the solar system, it becomes clear that its significance is not in what it offers for habitation, but in what it reveals about planetary science. It is a world where the sun dominates every aspect of existence, where time and temperature are stretched to extremes, and where ancient scars tell the story of a violent past. Mercury's resilience, orbiting so close to a star that could easily strip it bare, is a testament to the diversity and durability of worlds that form in the cosmic dance of gravity, heat, and motion. As we prepare to leave Mercury in our journey through the solar system, we carry with us a deeper appreciation for its harsh beauty. It is a place where the boundaries between day and night are not just shifts in light, but chasms of temperature, where the ground itself is a record of billions of years of celestial history, and where, despite the constant onslaught of solar radiation, the planet continues its silent orbit, a steadfast sentinel in the inner solar system. In the chapters ahead, we will move outward to the second planet from the Sun, a world shrouded in thick clouds, hotter than any other, and mysterious in its own right. If Mercury is the scorched metal heart of the solar system, this next destination is its smoldering toxic twin, Venus, Earth's toxic twin. If you were to look at Venus through a telescope, you might see a softly glowing, cream-colored sphere, serene and unchanging. Its surface remains hidden beneath a thick, unbroken layer of clouds that reflects sunlight so brilliantly that Venus shines as the brightest natural object in our night sky after the moon. For millennia, this beauty has captivated human observers. The ancient Greeks associated it with the goddess of love and beauty. The Romans gave it the same name. But behind its luminous veil lies one of the most hostile environments in the solar system, a place so hot and crushing that any visitor would be destroyed within minutes. Venus is often called Earth's twin because the two planets are similar in size, mass, and composition. Venus is just slightly smaller, with a diameter of about 12,100 kilometers compared to Earth's 12,742, and its density and gravity are close to our own. Both planets likely formed from similar materials in the same region of the solar system, but their paths diverge dramatically, creating two worlds that could not be more different in terms of climate and habitability. The key to Venus's infernal nature is its atmosphere, a thick, suffocating blanket of carbon dioxide with clouds of sulfuric acid. This atmosphere is over 90 times denser than Earth's, meaning the pressure at the surface is equivalent to being nearly a kilometer underwater in Earth's oceans. The result is an extreme greenhouse effect that traps heat so effectively that Venus has become the hottest planet in the solar system, with surface temperatures averaging around 465 degrees Celsius, hot enough to melt lead, zinc, or aluminum. Unlike Mercury, where temperatures drop sharply at night, Venus's thick atmosphere distributes heat evenly across the planet, making both day and night equally scorching. Venus also rotates in an unusual way. It spins on its axis in the opposite direction to most planets, a motion known as retrograde rotation. If you could stand on the surface, the sun would rise in the west and set in the east. But you'd have to be patient. Venus's rotation is extremely slow, taking about 243 Earth days to complete one spin. Strangely, its day is actually longer than its year, as it takes only 225 Earth days to orbit the sun. Despite this, the length of a Venusian day from sunrise to sunrise is about 117 Earth days due to the combined effects of rotation and orbital motion. From space, Venus's cloud tops appear calm and uniform, but closer inspection reveals a dynamic and turbulent atmosphere. Winds at high altitudes roar at speeds of up to 360 kilometers per hour, circling the planet in just 4 Earth days, in a phenomenon known as superrotation. Below the clouds, the winds slow dramatically, and near the surface, the atmosphere moves sluggishly, carrying only a faint breeze that would feel almost non-existent under such crushing pressure. The thick clouds consist mostly of sulfuric acid droplets, making Venus's skies corrosive as well as opaque. Sunlight can penetrate the clouds, but only dimly. Standing on the surface would be like being outside on a perpetually overcast day, tinted with a yellowish-orange hue. Visibility would be limited to a few kilometers, and the landscape would be bathed in a dull, ominous glow. The surface itself is a rocky desert of vast volcanic plains, towering mountains, and enormous lava flows. Radar mapping, conducted by missions such as NASA's Magellan spacecraft in the early 1990s, has revealed more than 1,000 large volcanoes and countless smaller ones. Some appear relatively young, suggesting that volcanic activity may still occur today. Indeed, in recent years, scientists have found evidence of changes in surface thermal patterns that could indicate active lava flows. If confirmed, this would make Venus one of the few volcanically active worlds in the solar system, alongside Earth and Jupiter's moon, Io. Among Venus's most striking features are its massive volcanic structures, such as Mat Mons and Sapis Mons, which rise several kilometers above the surrounding plains. There are also vast highland regions, like Ishtar Terra in the north and Aphrodite Terra near the equator, roughly comparable in size to continents on Earth. Between these highlands stretch low-lying plains covered by solidified lava, shaped by both volcanic and tectonic forces. Unlike Earth, Venus shows little evidence of plate tectonics, the large-scale movement of rigid crustal plates driven by mantle convection. Instead, its surface seems to have been resurfaced in catastrophic episodes, possibly when internal heat built up to the point that the crust weakened and allowed widespread volcanic flooding. Some scientists believe this could have happened as recently as 500 million years ago, effectively erasing most older geological features. Venus also has a fascinating, if unsettling, history in planetary science. For much of the 20th century, many imagined it as a lush, tropical world hidden beneath its clouds. This idea persisted until space probes began to reveal the truth. The Soviet Union's Venera program in the 1960s and 70s sent a series of spacecraft to Venus, some of which successfully landed and transmitted data from the surface, albeit only for minutes before succumbing to the intense heat and pressure. These landers confirmed the crushing atmosphere, the scorching temperatures, and the rocky terrain, dispelling any lingering notions of a habitable paradise. Despite its deadly conditions, Venus remains an object of great scientific interest. Its runaway greenhouse effect serves as a powerful example of climate change on a planetary scale. By studying Venus, scientists gain valuable insight into how atmospheres evolve and how planetary climates can shift dramatically over time. This knowledge has direct implications for understanding Earth's climate and predicting its long-term future. Another mystery is why Venus lost nearly all its water. Early in its history, Venus may have had oceans much like Earth's, but intense solar radiation likely stripped away its hydrogen, leaving oxygen to react with surface rocks or escape into space. Without water to moderate temperatures and drive plate tectonics, the planet's climate spiraled into its current state. Understanding exactly how and when this happened could reveal whether Venus was once habitable and how long it stayed that way. While the conditions on Venus's surface are extreme, the upper atmosphere presents a very different environment, one that has intrigued scientists for decades. Around 50 to 60 kilometers above the surface, the temperature and pressure become surprisingly Earth-like. At these altitudes, the temperature hovers around 20 to 30 degrees Celsius, and the pressure is close to 1 atmosphere. This has led to speculation about the possibility of floating research stations or even long-term human outposts in Venus's skies. Such platforms would still need to contend with corrosive sulfuric acid in the clouds, but the challenges there may be more manageable than those on the ground. Intriguingly, some researchers have speculated about the potential for microbial life in these upper cloud layers. While the surface is certainly inhospitable to life as we know it, the temperate regions of the atmosphere might offer niches where extremophile organisms, if they ever arose, could survive. In 2020, a controversial study reported the detection of phosphine gas in Venus's atmosphere, a molecule that, on Earth, is often associated with biological processes. Although later studies questioned and challenged the finding, the debate reignited interest in exploring Venus with new missions specifically designed to search for chemical signatures of life. The study of Venus also has a strong connection to exoplanet research. Many of the rocky planets discovered around other stars orbit much closer to their suns than Earth does to ours. As a result, they may share more in common with Venus than with Earth. Understanding Venus's geology, atmosphere, and history could therefore help astronomers interpret observations of these distant worlds and assess their potential habitability, or lack thereof. From an observational standpoint, Venus is a familiar sight to skywatchers. It is often visible in the morning or evening sky, earning it the nicknames Morning Star and Evening Star. Because it never strays far from the sun in the sky, Venus is most easily observed during twilight. When viewed through a telescope, Venus shows phases similar to the moon's, ranging from crescent to full, due to its position relative to Earth and the sun. These phases were famously observed by Galileo in 1610 and provided crucial evidence that planets orbit the sun, not Earth. In terms of exploration, Venus has been the target of numerous missions, particularly by the Soviet Union's Venera program, which achieved the first successful landing on another planet. Venera 7, in 1970, transmitted data from the surface for 23 minutes, confirming the crushing pressure and extreme heat. Later missions, like Venera 13 in 1982, sent back color photographs and analyzed soil samples before succumbing to the environment. NASA's Magellan mission, launched in 1989, used radar mapping to reveal the planet's detailed topography, transforming our understanding of its surface features. In the coming years, Venus will once again be a major focus for planetary exploration. NASA has announced 2 upcoming missions: Veritas, which will map the surface in high resolution to study its geology and search for signs of tectonic or volcanic activity, and Da Vinci Plus, which will plunge through the atmosphere to measure its composition and capture images of the surface during descent. The European Space Agency is also planning its Envision mission, which will investigate Venus's atmosphere, surface, and interior structure. Together, these missions could answer long-standing questions about how and why Venus became so different from Earth. For scientists, Venus represents both a warning and a mystery. It is a cautionary tale of how a planet's environment can become unrecognizably hostile, and a reminder that even Earth is not immune to profound climate shifts. At the same time, Venus challenges our understanding of planetary processes. Why does it lack plate tectonics? What drives its super-rotating winds? Could volcanic activity still be shaping its surface today? And most tantalizing of all, did it once harbor oceans and perhaps even life? Venus's story also has a certain poignancy. Here is a world that, in many ways, should have been Earth's sister, a planet of similar size and composition, formed in the same region of the solar system. Yet, a combination of factors, its position slightly closer to the sun, the loss of its water, and the runaway greenhouse effect, turned it into an inferno. This divergence underscores how delicate the balance of habitability can be, and how small differences in a planet's early conditions can lead to vastly different outcomes. From a human perspective, Venus is both captivating and forbidding. Its brilliance in the night sky has inspired myths, poetry, and art for thousands of years. Ancient cultures saw it as a symbol of love, beauty, and even war, depending on its appearance as the morning or evening star. In modern times, its harsh reality has not diminished its allure. Instead, the challenge of exploring Venus has become a testament to human ingenuity and persistence. If you could somehow survive a day on Venus, shielded in an indestructible suit, you would see a landscape unlike any other. The sky would be a thick, hazy orange, the sun just a faint glow through the clouds. The ground would be rocky and uneven, dotted with strange volcanic formations. The air would be crushing, and the heat would radiate from every direction. You might even see lightning flickering in the clouds above, the result of charged particles colliding in the dense atmosphere. Every step would be a reminder of the planet's overwhelming hostility and of the fine line that separates a habitable world from a dead one. As we prepare to leave Venus on our journey through the solar system, we carry with us lessons about climate, geology, and the fragility of habitability. Our next destination lies further out, where conditions are cooler, the atmosphere thinner, and the landscape marked by vast deserts and towering volcanoes. It is a world that has long fascinated scientists and the public alike, a planet that might once have been more Earth-like than it is today, and which continues to intrigue us with the possibility that it could one day host human explorers. Earth, our home and its unique features. From space, Earth appears as a shimmering blue and white sphere, suspended in the blackness of the cosmos. Its oceans reflect sunlight in dazzling shades of turquoise and deep indigo, while swirls of white clouds drift above the continents. It is a sight so striking that astronauts often describe it as life-changing, a vivid reminder of our planet's beauty and fragility. Yet beyond its outward appearance lies a complex, dynamic system unlike anything we have found elsewhere in the solar system, a world teeming with life, shaped by an intricate interplay of geology, atmosphere, water, and biology. Earth is the third planet from the Sun, orbiting at an average distance of about 150 million kilometers, a position that places it squarely in the so-called habitable zone, where temperatures allow liquid water to exist on the surface. This distance is not the only reason Earth is habitable, but it is a crucial factor. If we were significantly closer to the Sun, our oceans could boil away, as happened on Venus. If we were much farther, they could freeze, like the icy plains of Mars. Earth's position is part of a delicate balance that has allowed life to emerge and flourish for billions of years. Our planet is unique among the known worlds for having vast bodies of liquid water, covering about 71% of its surface. Water is essential for all known forms of life, and it also plays a central role in regulating Earth's climate. Oceans absorb heat, distribute it via currents, and influence weather patterns across the globe. They also act as a massive carbon sink, drawing carbon dioxide from the atmosphere and storing it for long periods, which helps stabilize the climate. The continents, which make up the remaining 29% of Earth's surface, are in constant motion, slowly drifting across the planet's surface due to plate tectonics. This process, driven by heat from Earth's interior, shapes mountains, opens oceans, and recycles crustal material back into the mantle. Plate tectonics also plays a vital role in the carbon cycle, helping regulate atmospheric levels of greenhouse gases and thus influencing long-term climate stability. Earth's atmosphere is another key factor in its uniqueness. Composed of roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases like carbon dioxide, methane, and argon, it provides the oxygen we breathe, shields us from harmful solar radiation, and traps enough heat to keep the planet warm through the greenhouse effect. The balance of these gases is maintained in part by life itself. Plants and photosynthetic microorganisms produce oxygen, while animals and other organisms release carbon dioxide. The atmosphere is also responsible for weather and climate. Driven by the sun's energy, air masses move across the globe, carrying moisture, heat, and nutrients. This circulation creates a diversity of climates, from tropical rainforests to arid deserts, and supports a staggering variety of ecosystems. The presence of liquid water and an atmosphere that protects and nourishes life sets Earth apart from all other planets we have explored. One of the most remarkable aspects of Earth is its biosphere, the sum of all living organisms and the ecosystems they inhabit. Life exists in an astonishing array of forms, from microscopic bacteria in deep ocean vents to towering redwood trees and vast herds of grazing animals. This diversity is the product of billions of years of evolution, shaped by changing environments, mass extinctions, and genetic adaptation. The interconnections between species and their environments form complex webs of relationships that sustain the planet's habitability. Earth's magnetic field is another critical feature, generated by the movement of molten iron in the outer core. This magnetic shield extends far into space, deflecting charged particles from the sun and protecting the atmosphere from being stripped away, as happened on Mars. The magnetic field also guides migratory animals, influences auroras, and helps maintain the conditions necessary for life to thrive. Our planet's history is one of constant transformation. From its formation 4.5 billion years ago, Earth has undergone dramatic changes. Oceans forming from condensed water vapor, continents assembling and breaking apart, and life evolving from simple single-celled organisms to the complex web we see today. There have been mass extinction events, such as the asteroid impact 66 million years ago that ended the reign of the dinosaurs, and ice ages that reshaped the land and life upon it. Each change has left its mark on the planet's geology, climate, and living systems. From a human perspective, Earth is not just our home. It is the only place we know where life exists. Our civilizations have risen and fallen within a relatively brief span of geological time. Yet our activities now have global impacts. We have altered landscapes, changed the composition of the atmosphere, and influenced the climate. These changes have sparked new scientific and ethical questions about how we care for our planet and ensure its health for future generations. Earth is also our launching point for exploring the universe. From here, we have sent spacecraft to other planets, telescopes into orbit, and humans to the moon. The vantage point of space exploration has given us a deeper appreciation of our planet's uniqueness and interconnectedness. The famous Earthrise photograph, taken by Apollo 8 astronauts in 1968, captured our world as a small, fragile oasis in the vastness of space, inspiring movements for environmental protection and planetary stewardship. Earth's climate system is one of its most defining and delicate features. Powered by the sun's energy, it is moderated by the planet's rotation, its axial tilt, the distribution of land and sea, and the presence of the atmosphere. Seasonal changes occur because Earth's axis is tilted at about 23.5 degrees relative to its orbit around the sun. This tilt ensures that different regions receive varying amounts of sunlight over the course of a year, creating the familiar rhythm of spring, summer, autumn, and winter. Without this tilt, much of the planet would experience minimal seasonal variation, altering the distribution and diversity of life. Weather patterns are shaped by complex interactions between the atmosphere, oceans, and land. Warm air rises at the equator, cools, and sinks at higher latitudes, creating circulation cells that transport heat and moisture around the globe. Ocean currents, like the Gulf Stream, move warm water from the tropics toward the poles, moderating climates in regions far from the equator. These interconnected systems make Earth a highly dynamic planet, where no 2 days are ever exactly the same anywhere on its surface. The biosphere plays an active role in maintaining Earth's habitability. Forests act as carbon sinks, drawing in carbon dioxide and releasing oxygen, while wetlands filter water and provide habitats for countless species. Coral reefs support an extraordinary diversity of marine life, and microorganisms in the soil contribute to nutrient cycling that sustains plant growth. Each ecosystem is part of a larger network, and disturbances in one can ripple through the rest. The ongoing loss of biodiversity due to human activity has drawn attention to how fragile this balance can be. Another unique aspect of Earth is its relationship with the Moon. Our large natural satellite not only creates tides that shape coastal ecosystems, but also helps stabilize Earth's axial tilt. Without the Moon, our tilt could vary wildly over millions of years, leading to extreme climate swings that might make life as we know it more difficult. The Moon also served as humanity's first stepping stone into space, providing valuable experience for future exploration beyond our planet. Geologically, Earth is still very much alive. Volcanoes erupt, forming new land and altering the atmosphere. Earthquakes reshape landscapes and remind us of the immense energy stored beneath our feet. Mountain ranges continue to rise where tectonic plates collide, while erosion and weathering slowly wear them down. These processes recycle materials between the surface and the deep interior, maintaining a balance that has persisted for billions of years. Earth's interior structure consists of a thin crust, a viscous mantle, a liquid outer core, and a solid inner core. Heat from radioactive decay and leftover energy from the planet's formation drives convection in the mantle, which in turn powers plate tectonics. The outer core's movement generates the magnetic field, creating a protective bubble around the planet that extends thousands of kilometers into space. Without this shield, the solar wind could strip away the atmosphere, as has happened to Mars, drastically altering surface conditions. Culturally, Earth is woven into the mythologies, beliefs, and traditions of every civilization. Ancient people saw it as the center of the universe, a fixed and unchanging foundation. Today we understand it as a small, dynamic world orbiting an ordinary star in a vast galaxy. Yet, it remains our only home. This shift in perspective has not diminished its significance. Instead, it has underscored the preciousness of our position in the cosmos. From a planetary science perspective, Earth serves as the baseline for understanding other worlds. We compare Mars's thin atmosphere, Venus's runaway greenhouse effect, and Titan's methane lakes to the conditions here. By studying our own planet, we refine our understanding of planetary climates, geology, and the potential for life elsewhere. Conversely, by studying other planets, we gain new insights into Earth's past and future. One of the most profound realizations in modern science is that Earth's systems are deeply interconnected. Changes in one area, such as deforestation in the tropics or melting ice in the Arctic, can have far-reaching effects on climate, ocean currents, and even weather patterns halfway around the globe. This interconnectedness means that safeguarding the planet requires a global perspective, one that recognizes our shared responsibility for its health. As humanity looks to the future, Earth will remain our anchor. Even if we establish colonies on the Moon, Mars, or beyond, our homeworld will always be the foundation of our civilization. Its resources, stability, and beauty are unmatched in our solar system. The challenge will be to preserve these qualities while meeting the needs of a growing and technologically advanced population. If you could view Earth from deep space, you would see a small blue dot against the vast darkness, a fragile speck holding all the history, life, and wonder we have ever known. The image made famous by the Voyager 1 spacecraft, known as the pale blue dot, captures this reality. In that photograph, Earth occupies less than a single pixel, yet it contains everything we cherish. It is a humbling reminder that, in the grand scale of the cosmos, our world is both insignificant in size and priceless in value. As we conclude our exploration of Earth in this journey through the solar system, we carry forward an understanding of what makes it so extraordinary. It is a planet in balance, where geology, atmosphere, oceans, and life itself work together to maintain conditions suitable for a rich diversity of organisms. It is a place of beauty, resilience, and complexity, qualities we must protect if we are to ensure that future generations can continue to call it home. Our next destination takes us outward once again, to a world that has long stirred our imagination. Red deserts, colossal volcanoes, and the tantalizing possibility of ancient life await us there. It is a place both familiar and alien, a neighbor that shares some of our planet's traits yet stands in stark contrast in many ways. The Moon, silent companion. If Earth is a vibrant living world, then the Moon is its quiet, steadfast partner, forever linked yet profoundly different. For billions of years, it has accompanied our planet on its journey around the Sun, a silent witness to the unfolding story of life on Earth. Its pale light has guided travelers, inspired myths, and shaped the rhythms of life itself through the steady pull of its gravity. From the earliest civilizations to the astronauts who set foot on its dusty surface, the Moon has been a source of wonder, curiosity, and discovery. The Moon is Earth's only natural satellite, and at about 1/4 of Earth's diameter, roughly 3,474 kilometers, it is unusually large compared to the size of its parent planet. This proportion is rare among moons in the solar system, and is part of what makes our lunar companion so significant. It orbits at an average distance of about 384,400 kilometers, close enough that it appears large in our sky, yet far enough that it takes light just over a second to travel between the two worlds. The Moon's origin is one of the most fascinating chapters in planetary science. The leading theory, known as the giant impact hypothesis, suggests that about 4.5 billion years ago, a Mars-sized body, nicknamed Theia, collided with the young Earth. The immense energy of the impact blasted huge amounts of molten rock into space, which eventually coalesced under gravity to form the Moon. This theory explains the similarities in composition between Earth's mantle and the Moon's surface rocks, as well as the Moon's relatively small iron core compared to its size. Since its formation, the Moon has had a profound influence on Earth. Its gravitational pull creates the tides, which not only shape coastlines, but also play a role in the life cycles of many marine species. Over long timescales, the tidal interaction between Earth and the Moon has also slowed Earth's rotation, lengthening the day from just a few hours in the planet's early history to the 24-hour cycle we experience now. Meanwhile, the Moon gradually drifts away from us at a rate of about 3.8 centimeters per year, a pace slow enough that it will remain in our sky for hundreds of millions of years to come. The Moon's surface tells a story of ancient violence and quiet endurance. It is covered with countless craters of all sizes, the scars of impacts from asteroids and comets. Without an atmosphere to shield it, the Moon has been exposed to the full force of cosmic bombardment for billions of years. The largest of these scars, the South Pole Aitken Basin, stretches about 2,500 kilometers across and plunges more than 8 kilometers deep, making it one of the largest known impact structures in the solar system. Between the craters lie vast dark plains known as Maria, Latin for seas. These are not bodies of water, but expansive basaltic plains formed by ancient volcanic eruptions. They are most prominent on the side of the Moon facing Earth, giving it the familiar pattern that people have likened to faces, animals, and other shapes in the Man in the Moon. The lighter, more heavily cratered regions are called the highlands, which are older and composed mostly of an orthosite rock. One striking feature of the Moon's geology is its lack of active plate tectonics. While Earth's surface is constantly reshaped by the movement of its crustal plates, the Moon has been geologically quiet for most of its history. However, it is not entirely dead. Small moonquakes still occur, likely caused by the gradual cooling and shrinking of its interior, or by tidal stresses from Earth's gravity. The Moon's environment is stark and unforgiving, with no atmosphere to retain heat or protect against radiation. Surface temperatures swing dramatically, from about 127 degrees Celsius in sunlight to minus 173 degrees Celsius in darkness. A lunar day lasts about 29.5 Earth days, meaning 2 weeks of continuous daylight, followed by 2 weeks of night. The lack of atmosphere also means that the sky is always black, even during the day, with the sun or Earth hanging brilliantly in stark contrast against the void. For all its silence, the Moon plays a crucial role in our understanding of the solar system. Because it has no weather, erosion, or significant geological activity to erase features, it preserves a record of billions of years of solar system history. The rocks and soil brought back by the Apollo missions have revealed insights into the Moon's composition, volcanic history, and the frequency of impacts over time. Human exploration of the Moon remains one of humanity's greatest achievements. In 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on another world, leaving boot prints in the lunar regolith that could remain undisturbed for millions of years. Over the next few years, Apollo missions brought back samples, deployed scientific instruments, and explored a variety of lunar terrains. These missions demonstrated that humans could live and work on another celestial body, if only for a few days at a time. Since then, robotic missions from various space agencies have continued to explore the Moon. Orbiters have mapped its surface in exquisite detail, landers have studied its geology, and rovers have scouted for resources such as water ice. Recent discoveries have confirmed the presence of water ice in permanently shadowed craters near the poles, regions that never receive direct sunlight and remain cold enough to preserve ice for billions of years. This resource could be vital for future human missions, providing drinking water, breathable oxygen, and even rocket fuel if the water is split into hydrogen and oxygen. In recent years, the Moon has re-emerged as a central target in plans for human space exploration. NASA's Artemis program aims to return astronauts to the lunar surface, this time with the goal of establishing a sustainable presence. Unlike the Apollo missions, which were brief visits, Artemis envisions building infrastructure such as habitats, power systems, and resource extraction facilities, steps toward using the Moon as a staging ground for deeper space missions, including journeys to Mars. Other nations are also intensifying their lunar ambitions. China's Chang'e program has successfully landed rovers and returned samples from the Moon, while India's Chandrayaan missions have mapped the polar regions and searched for water ice. Private companies are developing landers and technologies for lunar resource utilization. potentially creating a new era of international and commercial activity beyond Earth. One of the most scientifically valuable aspects of the moon is its far side, the hemisphere that always faces away from Earth due to tidal locking. This side is shielded from the constant noise of human-made radio transmissions, making it an ideal location for radio telescopes to study the universe in frequencies that are difficult or impossible to observe from Earth. Establishing observatories there could open entirely new windows on the cosmos, allowing astronomers to detect faint signals from the earliest epochs after the Big Bang. The moon's tidal locking is a direct result of its gravitational relationship with Earth. Over millions of years, the moon's rotation slowed until it matched its orbital period, ensuring that we always see the same face. While this creates the illusion that the moon is motionless in its orientation toward us, it actually rocks slightly back and forth in a motion called libration, allowing us to glimpse a bit more than a half of its surface over time. Culturally, the moon has left a deep imprint on humanity. It has been woven into myths, religions, and art across every civilization. Ancient calendars were based on its cycles, and its phases still influence traditions and festivals today. Poets have compared its light to love and longing, while scientists have looked at it as a stepping stone toward the stars. Even now, despite our modern understanding of its nature, the sight of a full moon rising over the horizon can evoke a sense of wonder that connects us with people across time and place. For scientists, the moon also serves as a laboratory for studying processes that affect all airless bodies in the solar system. Its surface is constantly bombarded by micrometeorites, which churn the top layer of soil into a fine powder called regolith. This regolith contains not only the story of lunar geology, but also particles from the solar wind and tiny fragments from distant asteroids and comets. By analyzing these materials, researchers can reconstruct aspects of the solar system's history that are otherwise inaccessible. The moon's gravitational pull continues to shape life on Earth in subtle ways. Beyond the tides, it influences the stability of our planet's axial tilt, which has a profound effect on long-term climate. Without the moon, Earth's tilt might vary chaotically, leading to extreme seasonal changes over geological timescales. This stability may have been crucial for the evolution of complex life, making the moon an unsung partner in Earth's biological story. Looking to the distant future, the moon may play a key role in humanity's survival and expansion. Its resources, such as water ice, metals, and abundant sunlight for solar power, could support off-world colonies. Its low gravity, about 1/6 that of Earth, makes it an ideal launch point for missions deeper into the solar system, requiring far less energy to escape its pull compared to Earth's. In this vision, the moon becomes not just a destination, but a gateway to the rest of the cosmos. If you were to stand on the moon and look back at Earth, you would see a sight unlike any other in the solar system. A brilliant blue and white sphere hanging in the blackness, glowing with the light of reflected sunlight. You would see continents, oceans, and swirling clouds in real time, the entire planet visible at once. This view, experienced firsthand by only a handful of astronauts, has been described as awe-inspiring, humbling, and transformative. It reminds us that our home is both beautiful and fragile, a singular oasis in a vast and often hostile universe. The moon, in its silence, has witnessed the entirety of Earth's story since its own birth. It has seen continents drift, ice ages come and go, life emerge and evolve, and humans rise to look back at it with eyes filled with curiosity. It will continue to circle our planet long after our species is gone, a constant companion marking the passage of time in the heavens. As we conclude our exploration of the moon, we turn our gaze outward once more. Our next destination lies beyond the orbit of our silent companion, into the realm of a world often called the Red Planet, a place that has captured human imagination for centuries, promising both scientific discovery and the tantalizing possibility of finding traces of life beyond Earth. Mars, the Red Planet. From Earth, Mars appears as a faint, reddish dot in the night sky, bright enough to be mistaken for a star, yet distinct in its hue. For centuries, it has fascinated astronomers, poets, and dreamers alike. The Romans named it after their god of war, inspired by its blood-like color. Today, it is one of the most studied worlds beyond our own, a planet that offers tantalizing hints of a past that might have been far more Earth-like than its current barren state. Mars is the fourth planet from the Sun, orbiting at an average distance of about 228 million kilometers. It is roughly half the size of Earth, with a diameter of about 6,779 kilometers, and only about 1/10 of Earth's mass. Its gravity is just 38% of what we experience here, light enough that you could leap more than twice as high as you can on Earth. Though you would also find that walking feels strangely floaty and deliberate. The planet's most distinctive feature, at least to the naked eye, is its color. This rusty red appearance comes from iron-rich minerals in the soil that have oxidized, creating a dusty coating that envelops the planet. Mars's thin atmosphere, made up mostly of carbon dioxide, is not dense enough to block much sunlight, so the surface is bathed in a soft, salmon-colored light. The sky itself often takes on a pinkish hue, though during sunrise and sunset, it can shift to brilliant blues due to the scattering of sunlight by fine dust particles. Mars has long been a subject of speculation about life. In the late 19th century, some astronomers believed they saw dark lines crisscrossing its surface, which they interpreted as artificial canals built by an intelligent civilization. We now know these were optical illusions, but the idea of life on Mars has persisted, fueled by the discovery that the planet once had flowing rivers, lakes, and possibly even oceans. Today, Mars is dry and cold, with average surface temperatures around -63 degrees Celsius, but the evidence for a wetter past is clear in its landscapes: winding river valleys, deltas, and mineral deposits that form only in the presence of water. The planet's polar ice caps are among its most striking features, made primarily of water ice. They also contain layers of frozen carbon dioxide, dry ice, that expand and contract with the seasons. During the Martian winter, temperatures can drop so low that carbon dioxide from the atmosphere freezes onto the surface, creating a temporary layer of frost. In summer, the dry ice sublimates back into the atmosphere, driving seasonal changes in atmospheric pressure. Mars is also home to some of the most extreme geological features in the solar system. Olympus Mons, for example, is the largest volcano known anywhere, standing nearly 22 kilometers high, about 3 times the height of Mount Everest, and spanning 600 kilometers across. It is so vast that its base could cover the entire state of Arizona. The planet also boasts Valles Marineris, a canyon system stretching over 4,000 kilometers, long enough to span the continental United States, and plunging up to 7 kilometers deep. These features speak to a geologically active past, though today Mars's interior appears largely dormant. Despite its smaller size, Mars shares some similarities with Earth. Its day, known as a sol, is just 24 hours and 37 minutes long, and its axial tilt of about 25 degrees gives it seasons much like ours, though each Martian year lasts nearly twice as long, about 687 Earth days. However, its thin atmosphere means that seasonal temperature swings are far more extreme, and its lack of a strong magnetic field leaves the surface exposed to high levels of radiation from the sun and cosmic rays. The absence of a global magnetic field is thought to be linked to the loss of Mars's thick atmosphere billions of years ago. Data from spacecraft like NASA's MAVEN mission suggests that the solar wind gradually stripped away the atmosphere after the planet's internal dynamo shut down. Without that protective shield, Mars's climate transformed from a potentially warm and wet world into the cold, arid desert we see today. One of the most exciting discoveries in Martian science has been the detection of seasonal methane emissions. On Earth, most methane comes from biological sources, though it can also be produced by geological processes. The fact that methane appears and disappears in Mars's atmosphere on a seasonal cycle raises intriguing questions, though we do not yet know whether its origin is biological or purely chemical. Mars has 2 small moons, Phobos and Deimos, which are likely captured asteroids. Both are irregularly shaped and heavily cratered, with Phobos orbiting so close to the planet that it rises and sets twice each Martian day. Over time, Phobos is slowly spiraling inward and will eventually break apart, possibly forming a ring around Mars. These moons are tiny compared to Earth's moon, but they could one day serve as stepping stones for human exploration of the planet. robotic exploration has revolutionized our understanding of Mars. NASA's Viking landers in the 1970s were the first to operate on the surface, conducting experiments to search for life. More recent rovers, Spirit, Opportunity, Curiosity, and Perseverance, have explored different regions, studying rocks, soils, and the atmosphere in unprecedented detail. These missions have confirmed the presence of ancient riverbeds, discovered organic molecules, and tested technologies for producing oxygen from the Martian atmosphere. Perseverance is even collecting samples that a future mission will return to Earth, potentially answering the question of whether life ever existed there. In addition to NASA, other space agencies are active on Mars. The European Space Agency, China's CNSA, India's ISRO, and the United Arab Emirates have all sent spacecraft to orbit or land on the planet. This global interest reflects Mars's unique combination of scientific intrigue and practical potential as a target for future human missions. Human exploration of Mars has long been a dream, and while no human has yet set foot on its surface, serious plans are underway to make it a reality. NASA's Artemis program, though focused on the Moon in the short term, is designed with the goal of preparing for Mars missions in the coming decades. Private companies, most notably SpaceX, have announced ambitious plans to send crews to the Red Planet, aiming for permanent settlements in the future. Such missions will face enormous challenges: the months-long journey, exposure to high radiation levels, the need for self-sustaining life support systems, and the psychological demands of isolation in a harsh environment. Despite these difficulties, Mars remains the most likely candidate for human colonization in the solar system. It offers resources such as water ice, which could be used for drinking, oxygen production, and even rocket fuel. Its day length is close enough to Earth's that human circadian rhythms could adapt without too much difficulty, and its gravity, while lower, is not so weak as to make long-term habitation impossible. Though we do not yet know how living in 38% gravity will affect human health over years or decades. One of the most compelling reasons to explore Mars is the search for life. While the surface today is hostile to most known organisms due to low atmospheric pressure, extreme cold, and high radiation, there may be habitable environments underground. Subsurface aquifers, if they exist, could provide stable temperatures and protection from radiation. Rovers have already found minerals that form in liquid water, suggesting that Mars once had conditions suitable for life. If we were to find even simple microbial fossils, it would be one of the most profound discoveries in human history, proving that life is not unique to Earth. Mars also serves as a natural laboratory for planetary science. Its preserved landscapes allow scientists to study processes that have been erased or altered on Earth by plate tectonics and erosion. For example, studying its craters helps refine our understanding of the solar system's impact history. Investigating its ancient riverbeds and lakebeds can reveal how climate changes unfold on a planetary scale. In this way, Mars is both a time capsule of the early solar system and a model for understanding the evolution of terrestrial planets. Dust is one of the planet's most persistent and challenging features. Fine particles coat nearly every surface and can be lifted into the atmosphere by winds, sometimes triggering massive planet-wide dust storms that last for weeks or months. These storms can obscure the surface from orbit, limit the efficiency of solar-powered spacecraft, and pose risks for future human explorers. Yet, they are also a fascinating atmospheric phenomenon, driven by the interplay of sunlight, surface heating, and the thin Martian air. The Red Planet's climate is shaped by its thin atmosphere, which is about 100 times less dense than Earth's. While this means less protection from radiation and less insulation to retain heat, it also allows for dramatic temperature swings between day and night, sometimes more than 60 degrees Celsius in a single day. Seasonal changes are influenced by Mars's axial tilt and its more eccentric orbit, leading to differences in seasonal lengths between the northern and southern hemispheres. Phobos and Deimos, though small, could play a role in Mars exploration. Establishing bases on these moons could provide a safer, lower-gravity environment for staging missions to the surface. Phobos, in particular, is close enough to Mars that astronauts could remotely operate robots on the surface in real time, avoiding the long communication delays faced by controllers on Earth. Culturally, Mars has had a unique place in human imagination. It has been the setting for countless novels, films, and works of art. From the canals imagined by Percival Lowell to the alien invasions of H.G. Wells's The War of the Worlds, and the colonization visions of contemporary science fiction. This fascination stems not only from its appearance and proximity, but also from the possibility that it could one day be a second home for humanity. International interest in Mars shows no signs of slowing. China has announced plans for sample return missions and eventual human landings. The European Space Agency is collaborating with NASA on the Mars Sample Return campaign. Robotic explorers continue to roam its surface and orbit overhead, sending back high-resolution images and streams of data that deepen our understanding with each passing year. If you could stand on Mars, perhaps near the rim of Valles Marineris, or on the slopes of Olympus Mons, the sight would be both alien and strangely familiar. The sun would appear smaller than it does on Earth, casting a dimmer, amber light. The thin atmosphere would make the sky a dusty butterscotch color during the day, fading to a deep, dark blue at sunset. At night, Earth might be visible as a bright star-like point, a reminder of the home left behind. As we prepare to leave Mars in our journey through the solar system, we do so with a sense of both excitement and humility. It is a planet that challenges us technologically, tempts us with the possibility of life, and stands as a bridge between the habitable zone we know and the colder, more distant realms beyond. Our next destination lies deep in those realms, where gas giants reign and worlds far larger than Earth hold court, surrounded by systems of moons that could rival planets in their own right. Jupiter, the giant among giants. If the solar system were a kingdom, Jupiter would be its colossal ruler, a world so massive that it could swallow all the other planets and still have room to spare. It is the largest planet in our solar system, a gas giant with a presence so dominating that its gravity shapes the orbits of asteroids, protects the inner planets from some comet impacts, and even influences the migration of other worlds during the early history of the solar system. Yet, for all its size and power, Jupiter is a place of mystery, an enormous sphere of swirling clouds and raging storms, without a solid surface to stand on. Jupiter orbits the Sun at an average distance of about 778 million kilometers, taking nearly 12 Earth years to complete one revolution. With a diameter of about 143,000 kilometers, it is more than 11 times wider than Earth. Its mass is more than twice that of all the other planets combined, accounting for about 70% of the solar system's planetary mass. Despite this immense size, Jupiter spins incredibly fast, completing a rotation in just under 10 hours. This rapid rotation causes the planet to bulge at the equator and flatten at the poles, a shape known as an oblate spheroid. The planet's appearance is dominated by its colorful bands of clouds, called zones and belts, which wrap around it parallel to the equator. These bands are made of ammonia ice crystals and other compounds, their colors ranging from white and beige to orange, red, and brown. The differences in color and texture are the result of complex atmospheric chemistry and varying altitudes of cloud layers. Strong winds, reaching speeds of up to 540 kilometers per hour, blow in opposite directions in adjacent bands, creating intense turbulence where they meet. One of the most iconic features in the entire solar system resides in Jupiter's atmosphere, the Great Red Spot. This vast storm, larger than Earth, has been raging for at least 350 years, possibly much longer. It is an anticyclonic storm, meaning it rotates counterclockwise in the southern hemisphere, with wind speeds that can exceed 400 kilometers per hour. In recent decades, the Great Red Spot has been shrinking, and scientists continue to study why its size and shape are changing over time. Jupiter's atmosphere is composed primarily of hydrogen and helium, much like the Sun, with trace amounts of methane, ammonia, water vapor, and other compounds. Beneath the visible clouds lies a layer of liquid molecular hydrogen, and deeper still, a layer of liquid metallic hydrogen, a bizarre state of matter in which hydrogen behaves like a metal due to the immense pressure. This metallic hydrogen layer is responsible for generating Jupiter's powerful magnetic field, the strongest of any planet in the solar system. This magnetic field creates a vast magnetosphere that extends millions of kilometers into space, enveloping several of Jupiter's moons and interacting with the solar wind. Within this magnetosphere, charged particles are trapped and accelerated, producing intense radiation belts that would be lethal to unprotected spacecraft. The field also drives spectacular auroras at Jupiter's poles, far brighter and more energetic than those on Earth. Jupiter has no solid surface in the traditional sense. As one descends through its atmosphere, the pressure and temperature increase dramatically, eventually transitioning into the dense liquid layers deep inside the planet. Any spacecraft attempting to land would be crushed and vaporized long before reaching any kind of core, which is thought to be composed of rock, metal, and hydrogen compounds under immense pressure. Surrounding Jupiter is a faint system of rings, composed mainly of dust particles ejected from its small inner moons by micrometeorite impacts. These rings are far less prominent than Saturn's, but still offer insight into the dynamics of the Jovian system. Perhaps the most remarkable aspect of Jupiter is its collection of moons, at least 95 confirmed as of today, ranging from tiny, irregularly shaped bodies to worlds larger than Mercury. The four largest, known as the Galilean moons, were discovered by Galileo Galilei in 1610 and remain some of the most fascinating objects in the solar system. Io, the most volcanically active body in the solar system, is covered with sulfur deposits and constantly reshaped by eruptions driven by tidal heating. Europa, with its smooth, icy surface, hides a global ocean beneath, making it one of the prime candidates in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, is bigger than Mercury and possesses its own magnetic field. Callisto, heavily cratered and ancient, preserves a record of the solar system's early history. Jupiter's immense gravity has played a major role in shaping the architecture of the solar system. In the early days, it may have migrated inward before moving back outward, scattering smaller bodies and influencing the formation of other planets. It also acts as a kind of cosmic shield for the inner planets, deflecting or capturing many comets and asteroids that might otherwise have threatened Earth. Though, in some cases, it can also send objects inward toward the Sun. Robotic missions have given us our best views of Jupiter and its moons. NASA's Pioneer and Voyager spacecraft provided the first close-up images, revealing the planet's complex cloud patterns and discovering its rings. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, studied its atmosphere, magnetosphere, and moons in unprecedented detail. More recently, NASA's Juno mission has been orbiting Jupiter since 2016, mapping its gravitational and magnetic fields, probing its interior structure, and capturing stunning images of its poles, which feature swirling cyclones unlike anything seen on Earth. Despite decades of study, Jupiter still holds many mysteries. How exactly did it form? What processes drive the long-term stability of its atmospheric patterns? Does its core resemble a solid object? Or is it a diffuse region where heavy elements mix with metallic hydrogen? The answers to these questions will not only deepen our understanding of Jupiter itself, but also of the countless gas giants orbiting other stars. Jupiter's influence extends far beyond its immediate surroundings. The Trojan asteroids, two vast swarms of rocky bodies that share Jupiter's orbit around the Sun, exist in regions known as Lagrange points, where the gravitational pull of Jupiter and the Sun is perfectly balanced. These asteroids are thought to be remnants from the early solar system, preserved in a relatively stable state for billions of years. Studying them could offer valuable clues about the building blocks that formed the planets. NASA's Lucy mission, launched in 2021, is currently on its way to explore several of these Trojans over the next decade. The planet's gravitational field also affects the orbits of comets, sometimes altering their paths dramatically. This has led to the idea that Jupiter acts as both a protector and a threat to Earth. Its massive presence can deflect dangerous objects away from the inner solar system. But it can also send some toward us if the conditions are right. In either case, it is clear that Jupiter's role in the cosmic balance of our neighborhood is a significant one. One of the most intriguing scientific targets in the Jovian system is Europa, which may harbor a salty ocean beneath its icy crust. kept liquid by heat generated from tidal flexing caused by Jupiter's gravity. Plumes of water vapor have been detected venting from its surface, suggesting that material from the ocean could be accessible for study without drilling through kilometers of ice. NASA's Europa Clipper mission, set to launch in the mid-2020s, will conduct detailed reconnaissance of Europa's surface and subsurface, searching for conditions that could support life. Io, in stark contrast, is a hellish world of constant volcanic eruptions, driven by the same tidal heating that warms Europa's ocean. Its surface is a kaleidoscope of sulfur deposits, lava flows, and volcanic pits, with some eruptions sending plumes hundreds of kilometers into space. The intense radiation environment near Jupiter makes Io one of the most challenging places to explore, but its extreme activity provides an unparalleled laboratory for studying volcanism in the solar system. Ganymede, with its own magnetic field, is another standout. This magnetic bubble interacts with Jupiter's larger magnetosphere, creating auroras in its thin oxygen atmosphere. Beneath its icy crust, Ganymede may also have a deep ocean, adding to the intrigue of potentially habitable environments among Jupiter's moons. Callisto, heavily cratered and ancient, appears geologically inactive, yet may still contain a subsurface ocean. The diversity of these moons makes the Jovian system almost like a miniature solar system in its own right, with a range of conditions and histories to explore. The scale of Jupiter's storms is another aspect that continues to fascinate scientists. In addition to the Great Red Spot, Juno has revealed the existence of massive cyclones at both poles, arranged in symmetrical patterns that have persisted for years. These polar storms are surrounded by smaller cyclones that seem to maintain stable positions, a phenomenon unlike anything in Earth's meteorology. Understanding how such storms form and remain stable could provide insights into atmospheric dynamics, not just on Jupiter, but on other gas giants and even exoplanets. Jupiter's role in exoplanet research is also significant. Many of the first exoplanets discovered were hot Jupiters, gas giants orbiting extremely close to their parent stars. Studying our own Jupiter provides a baseline for understanding these distant worlds, and for considering how the presence of a giant planet can affect the formation and evolution of smaller, potentially habitable planets in the same system. Culturally, Jupiter has inspired countless works of art, literature, and music. From ancient mythology, where it was associated with the Roman king of the gods and the Greek Zeus, to modern science fiction, where it serves as a setting for exploration and mystery, Jupiter has captured the human imagination for millennia. Even now, images from the Juno spacecraft, with their swirling marble-like cloudscapes, evoke a sense of awe and wonder that transcends scientific interest alone. Future exploration of Jupiter will likely focus not only on the planet itself, but also on its moons. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launching in the 2020s, will study Ganymede, Callisto, and Europa in detail, searching for signs of habitability and characterizing their environments. These missions will operate in one of the most challenging environments in the solar system, where intense radiation demands robust spacecraft shielding and careful mission planning. If you could approach Jupiter in person, the sight would be overwhelming. The planet would dominate the sky, filling it with shifting bands of cream, ochre, and crimson. Lightning storms, far larger than any on Earth, would flash within its clouds, illuminating the depths of its atmosphere. The Great Red Spot would loom like a planetary-scale hurricane, while the surrounding cloud belts would twist and churn endlessly. All around, its moons would glide silently in their orbits, each a world unto itself, each telling a different chapter in the story of the solar system. As we leave Jupiter behind on our journey, we head toward another giant, a planet adorned with rings so bright and graceful that they are visible even from Earth with the simplest telescope. This next stop in our voyage is not only one of the most visually stunning worlds in the solar system, but also a complex and dynamic system in its own right, with moons that rival planets in size and intrigue. Saturn, the Lord of the Rings. If Jupiter is the giant ruler of the solar system, Saturn is its elegant monarch, graceful, luminous, and instantly recognizable thanks to its breathtaking rings. Even small backyard telescopes reveal its beauty. A pale golden globe encircled by brilliant, delicate arcs of light. For centuries, Saturn has captivated astronomers and stargazers alike, not just for its striking appearance, but for the mysteries that surround its structure, its rings, and its diverse family of moons. Saturn is the sixth planet from the Sun, orbiting at an average distance of about 1.43 billion kilometers. It is the second largest planet in the solar system, with a diameter of roughly 120,500 kilometers, about 9.5 times that of Earth. Like Jupiter, Saturn is a gas giant composed mainly of hydrogen and helium, with traces of methane, ammonia, and other gases. Its mass, while immense, is only about 1/3 that of Jupiter, and its average density is so low, less than that of water, that it would float if a planet-sized ocean could somehow exist. The planet's rotation is rapid, completing one spin in just about 1.7 hours. This fast rotation, combined with its relatively low density, causes Saturn to bulge noticeably at the equator and flatten at the poles, a shape known as an oblate spheroid. Its upper atmosphere is arranged in bands similar to Jupiter's, though they are more subtle in color, with shades of yellow, gold, and beige. Winds in Saturn's atmosphere can reach incredible speeds, up to 1,800 kilometers per hour, making them some of the fastest in the solar system. The most iconic feature of Saturn, of course, is its ring system, composed primarily of countless particles of water ice, ranging in size from tiny grains to chunks several meters across. The rings are arranged in complex structures that extend more than 270,000 kilometers from the planet, but are only about 10 to 30 meters thick. The main rings, labeled A, B, and C, are separated by gaps such as the Cassini division, a dark band caused by gravitational interactions with Saturn's moons. Beyond the main rings lie fainter, more diffuse rings, some of which are fed by material from the planet's moons. The origin of Saturn's rings remains a topic of scientific debate. They may be remnants of a shattered moon or comet that ventured too close to the planet and was torn apart by tidal forces. Alternatively, they could be leftover material from the early solar system that never coalesced into a moon. Observations from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed that the rings are far more dynamic than previously thought. They are constantly shaped and reshaped by gravitational interactions with nearby moons, and they may be relatively young, perhaps only 100 million years old. Saturn's magnetic field, though weaker than Jupiter's, is still powerful and generates auroras at the poles. The planet's magnetosphere traps charged particles from the solar wind and from volcanic activity on its moon, Enceladus, creating a complex environment around the planet. Saturn is home to at least 146 moons, each with unique characteristics. The largest, Titan, is bigger than the planet Mercury and is one of the most intriguing worlds in the solar system. Titan has a thick atmosphere composed primarily of nitrogen, with methane clouds and surface lakes and rivers of liquid methane and ethane. Beneath its icy crust may lie a subsurface ocean of water mixed with ammonia, making Titan a potential habitat for life, albeit life very different from that on Earth. Enceladus, another of Saturn's moons, has drawn intense interest from scientists. Though only about 500 kilometers across, it possesses a global subsurface ocean beneath its icy shell. Geysers at its south pole eject water vapor, ice particles, and organic molecules into space, feeding material into Saturn's E-ring. The discovery of these plumes by Cassini has made Enceladus one of the most promising places to search for life beyond Earth, as the ejected material could be directly sampled by spacecraft without drilling through ice. Other moons add to the diversity of the Saturnian system. Mimas, with its large Herschel crater, looks strikingly like the fictional Death Star. Iapetus has a mysterious two-tone coloration, with one hemisphere much darker than the other. Hyperion, an irregularly shaped moon, has a spongy-looking surface covered in strange craters. Each of these worlds contributes to the richness of Saturn's realm, offering scientists a laboratory of planetary processes in miniature. The Cassini mission revolutionized our understanding of Saturn and its moons. Over its 13-year mission, Cassini observed seasonal changes in the planet's atmosphere, studied the intricate structures of the rings, and made close flybys of multiple moons. Its findings confirmed active geology on Enceladus, revealed the complex chemistry of Titan's atmosphere, and even captured the planet's shadow, stretching across the rings in stunning images. Cassini's mission ended in 2017 with a dramatic plunge into Saturn's atmosphere, a deliberate maneuver to avoid contaminating potentially habitable moons. Like Jupiter, Saturn likely has no solid surface. As one descends into its atmosphere, the pressure increases rapidly, transitioning from gaseous hydrogen to liquid hydrogen and eventually to metallic hydrogen at great depths. At the center may lie a core of rock and metal surrounded by layers of ice and hydrogen compounds, though this core remains hidden and difficult to study directly. Saturn's rings, while majestic, are not eternal. Observations from Cassini and earlier missions have shown that ring particles gradually spiral inward toward the planet, a process known as ring rain. This material is drawn in by Saturn's gravity and pulled down along magnetic field lines, eventually disappearing into the atmosphere. Based on current rates of loss, the rings may vanish in 100 to 300 million years, a brief moment in cosmic terms. This means that we are living in a rare era when Saturn's rings are still at their peak brilliance. The seasonal changes on Saturn are subtle but significant. Because the planet's axis is tilted by about 26.7 degrees, similar to Earth's, it experiences seasons during its 29.5-year orbit around the Sun. As the seasons shift, the ring's appearance changes when viewed from Earth, sometimes opening wide to display their full splendor, and other times appearing as a thin line when they are edge-on. These seasonal changes also affect the planet's atmosphere, with shifts in storm patterns and subtle changes in color as sunlight warms different hemispheres. Storms on Saturn can be massive and long-lasting. The most famous are the Great White Spots, gigantic storm systems that erupt roughly once every Saturnian year, or about every 30 Earth years. These storms can encircle the planet and persist for months, churning the atmosphere and leaving visible disturbances that last long after the storm has dissipated. Cassini observed one such storm in 2010, revealing complex interactions between atmospheric layers and showing that Saturn's weather is both violent and beautiful. Titan, Saturn's largest moon, deserves special attention. It is the only moon in the solar system with a dense atmosphere, and it is the only place besides Earth where stable liquids have been found on the surface. Instead of water, however, Titan's lakes and rivers are filled with liquid methane and ethane, part of an active hydrocarbon cycle similar to Earth's water cycle. Clouds form, rain falls, rivers carve valleys, and lakes and seas fill and evaporate. The presence of complex organic molecules in Titan's atmosphere and on its surface raises tantalizing questions about the potential for exotic forms of life. NASA's upcoming Dragonfly mission, set to launch in 2027, will send a rotorcraft to explore Titan's surface, flying between sites to study its chemistry, geology, and habitability. Enceladus continues to be one of the most compelling targets in the search for life. Cassini's flybys detected water-rich plumes that contain salts, simple and complex organic compounds, and even evidence of hydrothermal activity at the ocean floor. On Earth, hydrothermal vents support thriving ecosystems in the absence of sunlight, raising the possibility that Enceladus's ocean could host similar life forms. Future missions could sample the plumes directly to look for biosignatures, bypassing the need to drill through kilometers of ice. Beyond Titan and Enceladus, Saturn's moons exhibit a remarkable variety. Rhea may have a tenuous atmosphere of oxygen and carbon dioxide. Tethys features a massive canyon system, stretching over 2,000 kilometers. Dione shows signs of past tectonic activity, with bright icy cliffs cutting across its surface. Each moon adds another piece to the puzzle of how Saturn's system formed and evolved. The cultural and scientific significance of Saturn stretches back millennia. To ancient observers, it was the slowest moving of the visible planets, associated with time, discipline, and sometimes melancholy. In modern times, it has become a symbol of elegance and mystery. The images returned by Cassini, Saturn backlit by the sun, its rings glowing like a halo, with Earth appearing as a pale blue dot in the distance, have become iconic reminders of our place in the cosmos. Future exploration of Saturn will likely build on Cassini's legacy, focusing on its moons as potential habitats and on the long-term dynamics of its rings and atmosphere. Proposals include orbiters dedicated to studying Titan, probes to sample Enceladus's plumes, and even atmospheric entry missions to directly analyze Saturn's deep composition. Each new mission has the potential to deepen our understanding not only of Saturn, but also of the processes shaping giant planets across the galaxy. If you could stand on one of Saturn's moons, perhaps on the icy plains of Enceladus or the methane shores of Titan seas, the view would be unforgettable. Saturn would dominate the sky, a vast golden globe encircled by rings so bright they would cast shadows on the surface. The rings themselves would reveal intricate detail, gaps, waves, and countless icy particles orbiting in perfect harmony. It would be a scene both alien and serene, a reminder of the sheer diversity of landscapes within our own solar system. As we leave Saturn behind, we journey further into the cold, dim reaches of the solar system. Ahead lies a planet unlike any we have encountered so far, an ice giant tipped dramatically on its side, with a faint ring system and a set of moons orbiting in a tilted, almost whimsical arrangement. Our next stop will bring us to one of the most peculiar and overlooked worlds in the Sun's domain, Uranus, the tilted ice giant. If the planets of the solar system were characters in a cosmic story, Uranus would be the eccentric one, mysterious, understated, yet strikingly unusual in both appearance and behavior. From its pale cyan hue to its bizarre sideways rotation, Uranus defies many of the patterns seen in the other planets. For centuries, it was invisible to the naked eye, blending in with the faint background stars until it was finally recognized as a planet in 1781 by astronomer William Herschel. This discovery expanded the known boundaries of the solar system for the first time in recorded history. Uranus is the seventh planet from the Sun, orbiting at an average distance of about 2.87 billion kilometers. With a diameter of roughly 50,700 kilometers, it is the third largest planet in the solar system, yet it is significantly less massive than either Jupiter or Saturn. Classified as an ice giant, Uranus differs from the gas giants in its composition. While it contains hydrogen and helium, much of its mass is made up of water, ammonia, and methane ices, giving it a denser and colder nature. Its distinctive blue-green color comes from methane gas in the upper atmosphere, which absorbs red light and reflects the shorter blue and green wavelengths. Beneath this calm exterior lies a layered atmosphere of hydrogen, helium, and methane, transitioning into a slushy, icy mantle surrounding a small rocky core. Temperatures in Uranus's upper atmosphere can drop to minus 224 degrees Celsius, making it one of the coldest places in the solar system. Perhaps the most extraordinary feature of Uranus is its axial tilt. While most planets have tilts of less than 30 degrees, Uranus is tilted by about 98 degrees relative to its orbital plane, effectively rotating on its side. This means that for part of its 84-year orbit, one pole is pointed almost directly at the Sun, bathing that hemisphere in continuous daylight for decades, while the other endures equally long stretches of darkness. The cause of this tilt is likely a colossal collision with an Earth-sized body early in the planet's history, which may also explain the unusual arrangement of its moons and rings. The sideways rotation leads to highly unusual seasons. As Uranus moves around the Sun, the orientation of its poles changes dramatically relative to sunlight. During its solstices, one hemisphere experiences a constant day, while the other is locked in an unending night. At the equinoxes, the Sun rises and sets around the equator every 17 hours, the length of Uranus's day. These extreme seasonal shifts likely drive complex atmospheric dynamics that we are only beginning to understand. Uranus's atmosphere appears bland in visible light, with few features compared to the turbulent bands and storms of Jupiter and Saturn. However, infrared observations and high-contrast imaging have revealed faint cloud patterns, hazes, and occasional bright storms, particularly near the equator. Winds can reach speeds of over 900 kilometers per hour, and methane clouds form high in the atmosphere, drifting against the pale background. Surrounding the planet is a faint system of rings, discovered in 1977, when Uranus passed in front of a distant star, and astronomers noticed the starlight dimming multiple times before and after the planet itself crossed. These dark, narrow rings are composed mainly of large, icy particles coated with dark material. While far less prominent than Saturn's, they still offer clues to the planet's history and the influence of its moons. Speaking of moons, Uranus has at least 27 known satellites, many named after characters from the works of William Shakespeare and Alexander Pope. The five largest, Miranda, Ariel, Umbriel, Titania, and Oberon, are worlds of icy rock, each with distinct geological features. Miranda, the smallest of the five, is perhaps the most remarkable. It has towering cliffs, deep canyons, and patchwork terrains that suggest a history of violent geological upheavals, possibly driven by tidal heating in the past. Ariel shows signs of resurfacing from ancient cryovolcanism, while Titania and Oberon are heavily cratered with hints of tectonic activity. Despite Uranus's intriguing characteristics, it remains one of the least explored planets. Only one spacecraft, NASA's Voyager 2, has ever visited it, flying by in 1986. The encounter provided our only close-up images, revealing details about its atmosphere, rings, and moons, but left countless questions unanswered. We still know very little about Uranus's internal structure, the full dynamics of its atmosphere, or the exact composition and activity of its moons. Its magnetic field adds another layer of mystery. Unlike Earth's, which is closely aligned with its rotation axis, Uranus's magnetic field is tilted by about 59 degrees and offset from the planet's center. This creates a magnetosphere that wobbles and shifts dramatically as the planet rotates, leading to unusual patterns of charged particle motion and auroras. Understanding how such a field is generated could provide valuable insights into planetary magnetism, especially for ice giants and exoplanets with similar characteristics. In many ways, Uranus is a bridge between the familiar worlds of the inner solar system and the exotic outer frontier. Its chemistry and structure differ from those of the gas giants, yet it shares traits with Neptune, its distant sibling. Studying Uranus can help astronomers refine models of planet formation, especially for the many exoplanets discovered in the ice giant category. Uranus's tilted nature doesn't just affect its seasons, it also influences its ring system and the orbits of its moons. Because the planet essentially rolls around the sun on its side, the rings and moons follow this sideways alignment, creating a spectacle unlike any other in the solar system. During parts of its orbit, the rings are seen edge-on from Earth, becoming almost invisible, while at other times they open to reveal their narrow, dark arcs. These variations offer unique opportunities for astronomers to study how light interacts with the ring particles and how gravitational influences from the moons sculpt their structure. The moons of Uranus are diverse worlds, each telling its own story of formation and change. Miranda, with its 20-kilometer-high Verona-Rupes cliff, one of the tallest known in the solar system, looks as if it has been shattered and pieced back together multiple times. Theories suggest that Miranda may have been torn apart by gravitational forces and then reassembled, leaving behind its mismatched terrains. Ariel shows evidence of relatively recent geological activity, with smooth plains that may have been resurfaced by flows of icy material. Umbriel is darker and older, covered in impact craters, while Titania and Oberon, the largest of Uranus's moons, display a mix of ancient craters and younger fault lines, hinting at possible internal activity in the past. One of the big open questions is whether any of these moons might harbor subsurface oceans. Given what we have learned from moons like Europa and Enceladus, scientists speculate that some Uranian moons could have liquid water beneath their icy crusts, maintained by internal heat or residual tidal heating. If so, these hidden oceans could be potential habitats for life, even in the frigid outer solar system. Uranus's atmosphere is another area of active interest. While it appears calm in visible light, observations in infrared and through the Hubble Space Telescope have revealed that it is capable of dramatic outbursts. Bright storms have been spotted forming and fading within days, some stretching thousands of kilometers. These events may be linked to seasonal changes or to complex dynamics in the planet's deep atmosphere that remain poorly understood. Because of its distance and faintness, studying Uranus from Earth is challenging, and this is one reason why it remains so mysterious. The planet's long orbital period means that seasonal changes happen slowly, so slowly that no spacecraft has observed a complete Uranian year. For example, Voyager 2's flyby occurred near the planet's solstice, when one pole was fully illuminated, giving us only a snapshot of one seasonal extreme. Observing the planet across different points in its orbit would likely reveal major shifts in weather patterns and atmospheric structure. The scientific community has recognized the need for a dedicated mission to Uranus. The National Academy's Planetary Science Decadal Survey recently ranked a Uranus orbiter and probe as the top priority for the next flagship-class mission after Mars sample return. Such a mission would orbit the planet for several years, sending a probe into its atmosphere to directly measure temperature, pressure, composition, and wind speeds, while the orbiter would study the rings, moons, magnetosphere, and seasonal changes in unprecedented detail. From a cultural standpoint, Uranus has often been overlooked compared to the more visually striking Jupiter and Saturn, or the more romanticized Mars. Yet, for astronomers and planetary scientists, it holds a quiet allure. Its odd tilt, extreme seasons, and family of moons make it a world that challenges our understanding of planetary systems. In fact, many exoplanets discovered in recent years are similar in size and composition to Uranus, making it an ideal analog for studying distant worlds that we cannot yet visit. If you could travel to Uranus and observe it up close, the view would be ethereal. Its soft cyan glow would stand out against the blackness of space, with its delicate rings faintly shimmering in the sunlight. The planet would rotate slowly beneath you, its sideways spin giving the impression of a world that refuses to conform to the usual rules. Around it, its moons would drift in tilted orbits, each one an icy enigma, each one potentially hiding secrets beneath its frozen surface. Exploring Uranus is not just about curiosity, it's about filling a major gap in our knowledge of the solar system. With only a single brief flyby to inform us, there is so much we do not know. The depth and structure of its atmosphere, the true composition of its interior, the details of its magnetic field, and the potential habitability of its moons. Each answer could help us better understand the formation of ice giants, the diversity of planetary systems, and the possibilities for life in the coldest reaches of space. As our journey continues, we leave Uranus's tilted world behind and head toward the outermost planet in the solar system, a deep blue giant where supersonic winds whip across the surface and dark storms rage in the dim sunlight. Neptune awaits, a world of extremes and mystery, marking the final stop among the major planets before we venture to the fringes of the sun's domain. Neptune, the windy blue world. If the solar system were a vast ocean, Neptune would be its distant, mysterious horizon, remote, beautiful, and largely unexplored. It is the eighth and farthest known planet from the Sun, lying so far away that sunlight takes more than 4 hours to reach it. Shrouded in a deep blue haze and whipped by the fastest winds in the solar system, Neptune is a world of extremes, where the Sun is just a brilliant star in the dim sky and the seasons last for decades. Neptune orbits at an average distance of about 4.5 billion kilometers, completing one circuit around the Sun every 165 Earth years. With a diameter of about 49,250 kilometers, it is slightly smaller than its near twin, Uranus, but denser and more massive. Like Uranus, Neptune is classified as an ice giant, composed mainly of hydrogen, helium, and water, ammonia, and methane ices. Its striking deep blue color is caused by methane in the atmosphere, which absorbs red light, but scientists suspect that additional unknown components may contribute to its richer hue compared to Uranus's paler cyan. The atmosphere of Neptune is anything but tranquil. Winds reach speeds of up to 2,100 kilometers per hour, faster than the speed of sound in Earth's atmosphere. These supersonic winds drive massive storms, including dark spots reminiscent of Jupiter's Great Red Spot. The most famous of these, the Great Dark Spot, was first observed by the Voyager 2 spacecraft during its 1989 flyby. This storm was roughly the size of Earth, with bright white clouds of methane ice trailing around it like high-altitude cirrus clouds. When the Hubble Space Telescope looked again a few years later, the storm had vanished, only for other dark spots to appear in different regions. This suggests that Neptune's atmosphere is highly dynamic, with storms forming and dissipating over relatively short timescales. Neptune's internal heat plays a major role in driving its violent weather. Despite receiving less than 3% of the sunlight that Earth gets, Neptune emits about 2.6 times more energy than it absorbs from the Sun. This internal heat likely comes from the slow compression of the planet under its own gravity and the residual warmth from its formation. Combined with the planet's rapid rotation, completing a day in just 16 hours, this heat fuels powerful convection currents and the extreme winds that circle the planet. Beneath Neptune's atmosphere lies a mantle of hot, dense fluids composed of water, ammonia, and methane, sometimes described as a slush or superionic state, where water conducts electricity. Deeper still, a small rocky core may sit at the planet's center, though direct measurements remain elusive. The pressures and temperatures within Neptune are so extreme that some scientists believe methane in the mantle could break apart, allowing carbon atoms to form diamond crystals that rain downward into the interior, a phenomenon sometimes called diamond rain. Surrounding Neptune is a faint but complex ring system composed of dark, dusty material. The rings are clumpy and uneven, likely held together by the gravitational influence of small moons embedded within them. The outermost ring is particularly notable for having bright arcs, localized regions of higher particle density. These arcs were a puzzle for years, as orbital mechanics suggested they should quickly spread out and disappear. Observations now suggest that nearby moons, such as Galatea, help confine the arcs through gravitational interactions. Neptune has at least 14 known moons, the largest and most intriguing of which is Triton. Unlike most large moons which orbit in the same direction as their planet's rotation, Triton moves in a retrograde orbit, meaning it travels the opposite way. This unusual motion suggests that Triton was once a separate object, perhaps a dwarf planet from the Kuiper Belt, that was captured by Neptune's gravity. Triton is slightly smaller than Earth's moon, but far more active. Voyager 2 revealed icy plains, frozen lakes, and even geysers erupting nitrogen gas into the thin atmosphere. These geysers are thought to be powered by seasonal heating from the sun, which causes nitrogen ice near the surface to sublimate and build up pressure beneath a translucent layer of ice until it bursts through. Triton's surface is one of the coldest in the solar system, with temperatures around -235 degrees Celsius. Yet it is geologically young, with relatively few impact craters. This suggests active resurfacing, possibly driven by tidal heating from Neptune's gravity. Beneath its icy crust, Triton may harbor a subsurface ocean of liquid water, making it another prime target in the search for extraterrestrial life. Voyager 2's 1989 flyby remains our only close encounter with Neptune. In just a few hours, it transformed the distant blue speck into a richly detailed world, revealing storms, rings, and moons that had been invisible from Earth. Since then, advances in telescope technology, particularly with the Hubble Space Telescope and ground-based observatories using adaptive optics, have allowed astronomers to monitor Neptune's atmosphere and discover new moons. Still, much about the planet remains unknown, and many scientists advocate for a dedicated orbiter mission to study it in detail. Neptune's magnetic field is as unusual as Uranus's, tilted by about 47 degrees relative to its rotation axis and offset from the planet's center. This creates a magnetosphere that wobbles dramatically as the planet spins, influencing the behavior of charged particles and producing auroras at unexpected locations. Understanding this field could shed light on the internal structure and dynamics of ice giants, as well as on the magnetic environments of exoplanets with similar characteristics. The seasons on Neptune change so slowly that, since its discovery in 1846, it has completed less than one orbit around the Sun. Each season lasts more than 40 Earth years, and the slow shift in sunlight likely influences atmospheric patterns over decades. Observations over the last few decades have hinted at gradual changes in cloud cover and storm activity, but a long-term mission would be needed to confirm and understand these trends. Triton, Neptune's largest moon, remains one of the most compelling destinations in the outer solar system. Its retrograde orbit means that it is slowly spiraling inward toward Neptune. In about 3.6 billion years, it will either crash into the planet or be torn apart by tidal forces, potentially forming a spectacular new ring system. This distant fate, however, is just one part of Triton's intrigue. Beneath its frozen crust, there could be a salty subsurface ocean kept warm by tidal heating, offering the potential for life in one of the coldest environments imaginable. The geysers observed by Voyager 2, shooting nitrogen gas and dust kilometers high, provide direct evidence of internal activity, remarkable for a world so far from the Sun. Neptune's other moons, though smaller, are equally fascinating in their diversity. Nereid, with its extremely elongated orbit, swings from 1.4 million kilometers to more than 9.6 million kilometers away from Neptune, suggesting it may have been disturbed by Triton's capture. Proteus, the second largest moon, is irregular in shape and heavily cratered, resembling a giant boulder more than a sphere. Smaller moons like Despina, Thalassa, and Naiad orbit close to the planet, their gravitational influence helping to shape and stabilize the rings. Each of these moons contributes a piece to the story of how Neptune's system formed and evolved over billions of years. The planet's atmosphere, while stunning from a distance, is a violent and alien place up close. The supersonic winds are joined by rapid vertical movements of air, driving the formation of towering clouds of methane ice crystals. These clouds can appear and vanish in a matter of hours, their brilliant white tops contrasting sharply with Neptune's deep blue background. The storms themselves may be powered not just by the planet's internal heat, but also by complex interactions between atmospheric layers and the dynamics of its unusual magnetosphere. Neptune's distance from the Sun means that solar energy alone cannot account for its active weather. This has led scientists to propose that the planet's internal structure is more dynamic than previously thought, possibly involving convective currents in its hot, icy mantle. The heat from these currents may rise to the surface in bursts, fueling temporary but intense weather patterns. While Neptune may seem far removed from our daily lives, studying it has broader implications for understanding planets across the galaxy. Many exoplanets discovered so far fall into the Neptune-like category, worlds similar in size and mass to our ice giants. By studying Neptune in detail, we can better interpret the faint signals we detect from these distant planets, helping to determine their compositions, climates, and potential for hosting moons, or even life. From a cultural and historical perspective, Neptune is notable for being the first planet discovered through mathematics rather than direct observation. In the mid-19th century, astronomers noticed that Uranus's orbit did not match predictions based on Newton's laws. Calculations by French mathematician Urbain Le Verrier and British mathematician John Couch Adams independently suggested the presence of another massive planet tugging at Uranus. When German astronomer Johann Galle pointed his telescope at the predicted position in 1846, Neptune was found within a single degree of the calculated location, a triumph of celestial mechanics that stands as one of the great achievements in the history of science. Future exploration of Neptune has long been a dream for planetary scientists. A dedicated orbiter could map its atmosphere over many years, study its magnetosphere in detail, and conduct multiple flybys of Triton to search for signs of habitability. Concepts for such missions often include atmospheric probes to directly sample Neptune's winds, clouds, and composition. Triton, in particular, would be a prime target for a lander, or even a cryobot, an autonomous probe capable of melting through ice to reach a subsurface ocean. If you could stand on Triton's icy plains and look up at Neptune, the view would be unlike anything on Earth. The planet would dominate the sky, glowing in deep blues and aquamarines, its faint rings casting subtle shadows. From this vantage point, you would see a world in constant motion. Clouds racing around the planet at incredible speeds, storms swirling in the dim sunlight. The sun itself would appear as only a bright star, yet Neptune's own beauty would more than compensate for the distance. As we prepare to leave Neptune, we approach the very edge of the sun's realm. Beyond this point lies a frontier filled with icy remnants of the solar system's formation. Dwarf planets, comets, and countless smaller bodies drifting in the dark. Our final chapter will take us past the orbit of Neptune into the Kuiper Belt and beyond, to the frozen boundaries where the sun's influence begins to fade into interstellar space. Beyond Neptune, dwarf planets, asteroids, and the edge of the solar system. Leaving Neptune behind, our journey takes us into a realm where sunlight fades into a pale glow, and the solar system transitions into deep space. This is the domain of the Kuiper Belt, a vast icy expanse that stretches billions of kilometers beyond Neptune's orbit. Here, countless frozen bodies, ranging from tiny fragments to worlds the size of moons, drift in slow, cold orbits. They are remnants from the early days of the solar system, leftover building blocks that never coalesced into a full-fledged planet. The Kuiper Belt begins at roughly 30 astronomical units, AU, from the Sun, and extends to about 50 AU, though some definitions stretch it even farther. Its population includes short-period comets, icy asteroids, and several recognized dwarf planets, among them Pluto, Haumea, Makemake, and Eris. These bodies are rich in volatile materials such as water ice, methane, nitrogen, and ammonia, preserved in their frozen state for over 4.5 billion years. Studying them is like opening a time capsule from the birth of the solar system. Pluto, once considered the ninth planet, remains the best-known resident of this distant region. Discovered in 1930 by Clyde Tombaugh, Pluto was reclassified as a dwarf planet in 2006, after the International Astronomical Union defined the term planet more strictly. While its demotion sparked debate and emotion, the New Horizons spacecraft's 2015 flyby showed that Pluto is far from insignificant. The encounter revealed a world with towering ice mountains, smooth nitrogen plains, and a thin, layered atmosphere. The heart-shaped region, informally named the Tombaugh Regio, became an instant symbol of Pluto's charm. Beneath its surface, there may even be a subsurface ocean of liquid water, kept from freezing by residual heat and possibly salts. Beyond Pluto lies Eris, a slightly smaller but more massive dwarf planet discovered in 2005. Its discovery was one of the catalysts for the planet definition change. Eris orbits much farther from the Sun, taking over 500 years to complete a single orbit. Its surface is coated with frozen methane, making it one of the brightest objects in the solar system. Eris also has a small moon named Dysnomia, which helps scientists measure its mass and density. Haumea stands out for its unusual shape, an elongated ellipsoid likely caused by its rapid rotation, which completes in less than 4 hours. It also has a pair of moons and a faint ring system, making it the only known dwarf planet with such a feature. Its surface is covered in crystalline water ice, suggesting either past resurfacing or ongoing geological processes. Makemake, another bright dwarf planet, orbits near the outer edge of the Kuiper Belt. It has a reddish color from organic molecules known as tholins, formed when sunlight interacts with methane ice. In 2016, astronomers discovered a tiny moon orbiting Makemake, revealing that even these distant bodies can host miniature systems of their own. The Kuiper Belt is not uniform. Its objects are grouped into different populations based on their orbital characteristics. Some have nearly circular orbits that lie close to the plane of the solar system, while others follow more eccentric and inclined paths, suggesting that gravitational interactions with Neptune and perhaps other massive bodies have shaped their current positions. One of the most intriguing aspects of the Kuiper Belt is its connection to the idea of Planet 9, a hypothetical world, perhaps 5 to 10 times the mass of Earth, lurking far beyond Neptune. The orbits of certain distant Kuiper Belt objects appear to be clustered in a way that could be explained by the gravitational pull of such a planet. If it exists, Planet 9 would orbit hundreds of astronomical units from the Sun, taking thousands of years to complete a revolution. Its discovery would once again redefine our view of the solar system's structure. Beyond the Kuiper Belt lies the scattered disk, a region of icy bodies with highly elongated and tilted orbits. These objects can be flung far from the Sun, sometimes into the inner solar system, becoming comets. Still farther out, at distances of thousands to tens of thousands of astronomical units, is the Oort cloud, a vast spherical shell of icy bodies that is thought to be the source of long-period comets. While no Oort cloud object has been directly observed, its existence is supported by the orbits of comets that arrive from all directions in the sky. Asteroids, though more concentrated in the main belt between Mars and Jupiter, also have populations in the outer solar system. These include the Trojan asteroids, which share the orbits of giant planets, particularly Jupiter and Neptune, and centaurs, icy rocky bodies whose unstable paths cross the orbits of the giant planets. Centaurs, such as the famous 2060 Chiron, are thought to be former Kuiper Belt objects migrating inward. Spacecraft exploration of the outer solar system's small bodies has been limited but groundbreaking. Besides New Horizons' Pluto flyby, the spacecraft also visited Arrokoth in 2019, the most distant object ever explored up close. Arrokoth is a contact binary, two lobes gently fused together, shaped like a snowman, flattened by billions of years of slow evolution. Its pristine surface offers a glimpse of the processes that built the planets. These far-off regions are not just scientifically interesting. They also mark the boundaries of the sun's influence. The heliosphere, a bubble of charged particles blown by the solar wind, extends far beyond the planets, but eventually gives way to the interstellar medium. The Voyager 1 and Voyager 2 spacecraft have both crossed this boundary known as the heliopause, entering interstellar space. Yet, even now, they remain within the sun's gravitational reach, which extends to perhaps halfway to the nearest star. Life in the Kuiper Belt and beyond moves at an almost glacial pace. Objects out here orbit so slowly that their positions barely shift in a human lifetime. Yet, over millions of years, gravitational nudges from Neptune or passing stars can send them on entirely new trajectories. Sometimes these perturbations fling an icy body inward toward the sun, where it may become an active comet, developing a glowing coma and a streaming tail as volatile ices vaporize. Other times, these nudges send bodies outward into the deep freeze, possibly never to return. Comets are among the most visible ambassadors from these outer realms. Short-period comets, such as Halley's Comet, are believed to originate in the Kuiper Belt, while long-period comets, those taking thousands of years to orbit the sun, are thought to come from the Oort cloud. When these icy visitors approach the sun, they offer scientists rare opportunities to study material preserved from the solar system's earliest days. Each comet's composition, structure, and behavior tells a piece of the story of how our planetary neighborhood formed. The scattered disk, lying beyond the main Kuiper Belt, is populated with objects whose orbits are stretched into long ellipses. These worlds are among the most isolated in the solar system, spending much of their orbits far from the sun, then briefly swinging inward before retreating again into the dark. The largest known scattered disk object is Eris, but many others remain undiscovered due to their vast distances and faintness. Their extreme orbits suggest a violent past, possibly the result of gravitational encounters with Neptune, or even the hypothesized Planet 9. The Oort cloud, if we could see it, would appear as an immense spherical swarm of icy nuclei surrounding the sun. Its inner boundary may begin around 2,000 astronomical units, while the outer edge could extend as far as 100,000 astronomical units, nearly halfway to Proxima Centauri, the nearest star. It is believed to contain trillions of icy bodies, leftovers from the solar system's formation, that were flung outward by the gravitational influence of the giant planets. Most will remain there forever, but some are occasionally dislodged by passing stars or the tidal forces of the Milky Way, sending them inward as long-period comets. At these distances, the sun is little more than a bright star in the sky, providing almost no warmth. Temperatures in the Oort cloud may hover just a few degrees above absolute zero, yet the gravitational pull of the sun still binds these objects, marking the true extent of our solar system. Beyond this lies interstellar space, vast, cold, and mostly empty, but not entirely devoid of matter. Here, thin clouds of gas and dust drift between the stars, occasionally enriched by supernova explosions or the winds from massive stars. The edge of the sun's influence is defined in several different ways. The heliopause marks where the solar wind is balanced by the pressure of the interstellar medium. The gravitational boundary, called the Hill sphere, extends much farther, encompassing even the distant Oort cloud. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, making them humanity's first emissaries to interstellar space. Yet their journey continues. They will orbit the galaxy alongside the stars for billions of years, carrying with them the golden records, messages from Earth intended for any intelligent life that might encounter them. One of the enduring questions about these distant regions is whether they could harbor life. While the conditions are harsh and sunlight is weak, some scientists speculate that subsurface oceans could exist within larger Kuiper Belt objects insulated by thick ice and warmed by radioactive decay. If so, microbial life could persist in these hidden oceans, much as it might on moons like Europa or Enceladus. Detecting such life would be challenging, requiring landers or penetrators capable of drilling through kilometers of ice in a realm where solar power is nearly useless. Exploration of these regions will be difficult but not impossible. Future spacecraft may use advanced propulsion systems, such as nuclear electric propulsion or solar sails, to reach the Kuiper Belt in a matter of years instead of decades. Missions could conduct flybys of multiple objects, mapping their surfaces, analyzing their compositions, and searching for signs of activity. Some proposals even envision spacecraft that could rendezvous with a comet or Kuiper Belt object, study it for months, and then continue onward to another target. In many ways, the Kuiper Belt, scattered disk, and Oort cloud are the frontier of planetary science. They are places where the rules of the inner solar system no longer apply, where sunlight is a luxury, and where time seems to stretch into infinity. Yet they are also the archives of our cosmic past, holding untouched records of the conditions from which the sun and planets emerged. As our journey through the solar system comes to an end, we find ourselves standing metaphorically at its boundary, gazing outward into the galaxy. Behind us lies a chain of worlds, each with its own story, from the scorched plains of Mercury to the icy deserts of Pluto and beyond. Ahead lies the endless sea of interstellar space, dotted with distant stars and perhaps other planetary systems, each with its own mysteries. Here, at the edge, we are reminded of both our smallness and our significance. The solar system is vast, but it is just one among billions in the Milky Way, which itself is only one galaxy among countless others. And yet, for us, it is home, a place of beauty, complexity, and wonder. Our voyage may end here for now, but the story of exploration continues. One day, humanity may send probes to explore the Oort cloud, to touch the icy hearts of comets, or even to travel beyond the sun's gravitational reach. Until then, we can look up at the night sky, knowing that out there, far beyond the planets we can see, lies a realm of frozen worlds waiting patiently for their turn in the light. I hope you enjoyed this journey through the solar system. If you're still awake, there's another relaxing voyage waiting for you right here on the screen. A perfect next stop for your cosmic adventure. Until we meet again among the stars, take care and have a peaceful night.